What makes a planet horrifying in space terms? When astronomers peer into the vast cosmos, they discover worlds so extreme and hostile that they defy our earthly imagination. These aren't simply uninhabitable planets. They're cosmic nightmares where the laws of physics create conditions so violent and alien that they would destroy any human visitor within seconds. The universe, in its infinite creativity, has crafted environments so fundamentally different from Earth that they challenge our very understanding of what a planet can be. The hostile and extreme conditions of exoplanets often surpass our darkest science fiction. Some worlds experience temperatures that would melt spacecraft instantly, exceeding 2000 degrees Celsius, while others have atmospheric pressures that would crush diamond like it was made of paper, hundreds or even thousands of times the pressure at Earth's sea level. There are planets where it rains molten metal, forming scorching puddles that would vaporize human flesh on contact. Some worlds are shrouded in toxic gases that would dissolve lungs in moments, while other cosmic bodies are bombarded by lethal radiation at levels thousands of times what would kill a human. These aren't just inhospitable environments, they're active death traps crafted by the universe's most extreme forces. The cosmos seems almost deliberately designed to create these hellscapes. Gas giants that migrate too close to their stars become hot Jupiters, with winds reaching thousands of kilometers per hour. Rocky planets positioned at the wrong distance turn into pressure cookers with surface temperatures capable of melting lead, zinc, and even iron. Some planets orbit their stars so closely that their surfaces are locked in eternal daylight on one side and perpetual darkness on the other, creating dramatic temperature differences that drive apocalyptic weather systems. Others experience tidal forces so extreme that they're continuously stretched and compressed, generating enough frictional heat to keep entire oceans in a perpetual molten state. To truly appreciate the horror of these worlds, we must first understand the delicate balance that makes Earth habitable. Our planet exists in a narrow Goldilocks zone around the Sun, not too hot, not too cold, allowing water to exist in liquid form. Our atmosphere contains just the right mix of gases to trap enough heat while allowing excess to escape, maintaining global temperatures within a range conducive to life. Earth's magnetic field shields us from deadly solar radiation, while our planet's mass creates a gravitational pull strong enough to hold an atmosphere, but not so strong that it crushes organic life. This perfect balance is exceedingly rare in the cosmos. Most planets, it seems, exist in states of extreme imbalance. Some form too close to their stars, creating furnace-like conditions where rocks melt into lava seas. Others form too far away, becoming frozen worlds where temperatures plunge hundreds of degrees below freezing, turning gases into solids and creating landscapes of frozen nitrogen and methane. Some planets grew too massive, their gravitational fields crushing everything on their surfaces, while others remain too small, unable to hold onto atmospheres or generate the internal heat needed for geological activity. The physical laws governing these extreme worlds are the same ones that apply on Earth. Thermodynamics, gravity, electromagnetic forces, but their manifestations are so extreme as to seem alien. Water, the gentle liquid essential to life on Earth, becomes a supercritical fluid under extreme pressure and temperature, with properties between a liquid and a gas. Hydrogen, normally a gas in Earth conditions, can behave like a metal under extreme pressure. Common substances like methane and ammonia, which exist as gases on Earth, form lakes and oceans on worlds cold enough to liquefy them. How do astronomers find and study these terrifying worlds? The technology to detect these cosmic horrors has only emerged in recent decades. Space telescopes like Kepler, TESS, and the James Webb Space Telescope have revolutionized our ability to spot planets orbiting distant stars. By measuring tiny dips in starlight as planets pass in front, a technique called transit photometry, scientists can determine a planet's size. By detecting the slight gravitational wobble these worlds cause in their host stars, a method called radial velocity, astronomers can calculate a planet's mass. Together, these measurements reveal a planet's density, offering clues about its composition, whether it's a gas giant like Jupiter, a rocky world like Earth, or something more exotic. The transit method, which has discovered the majority of known exoplanets, is remarkably sensitive. A planet like Earth passing in front of a star like our Sun blocks only about 1/10,000th of the star's light, an almost imperceptible dimming that requires extremely precise instruments to detect. Yet modern telescopes can not only spot this tiny change in brightness, but can also measure how the dimming varies across different wavelengths of light, providing insights into a planet's atmospheric composition. The radial velocity method, meanwhile, detects the subtle wobble a planet induces in its parent star. All orbiting bodies, planets and stars alike, actually orbit around their common center of mass. For a star-planet system, this means the star itself moves in a small circle or ellipse as the planet orbits around it. The resulting periodic shifts in the star's position cause equally periodic shifts in the wavelength of light it emits, a phenomenon known as the Doppler effect. When the star moves toward Earth, its light waves become compressed, shifting toward the blue end of the spectrum. When it moves away, its light waves stretch out, shifting toward the red. By measuring these tiny spectral shifts, astronomers can determine the mass of the planet causing the wobble. But the true breakthrough in understanding these nightmare worlds comes from analyzing their atmospheres. When a planet transits its star, a tiny fraction of starlight passes through the planet's atmospheric envelope. Different molecules in that atmosphere absorb specific wavelengths of light, creating a unique spectral fingerprint. Through this technique, astronomers have detected clouds of glass, vaporized metals, and acid rains on planets trillions of miles away. Computer models then help scientists understand the horrifying conditions these chemical signatures imply, painting pictures of worlds that challenge our understanding of what's possible in the universe. The process of atmospheric analysis is extraordinarily complex. The light from the planet's atmosphere represents only a tiny fraction of the total light received from the star-planet system. Extracting this signal requires not only sophisticated instruments, but also advanced statistical techniques to separate the planetary signature from stellar variability, instrument noise, and other confounding factors. Yet, through persistence and innovation, astronomers have succeeded in identifying specific molecules, including water vapor, methane, carbon dioxide, and even exotic compounds like titanium oxide, in the atmospheres of distant worlds. The James Webb Space Telescope, launched in 2021, has taken this analysis to new heights. With its unprecedented infrared sensitivity, it can detect atmospheric compositions with greater precision than ever before, revealing the chemical makeup of exoplanets in extraordinary detail. This technological marvel has accelerated our understanding of these distant worlds, confirming theoretical models and sometimes revealing surprises that force scientists to reconsider their assumptions about planetary formation and evolution. Ground-based telescopes contribute to this research as well. The European Southern Observatory's Very Large Telescope in Chile, the W.M. Keck Observatory in Hawaii, and other major observatories have developed specialized instruments specifically designed to study exoplanets. These include high-resolution spectrographs capable of detecting minute Doppler shifts and coronagraphs that block out the intense light from stars to allow direct imaging of the much fainter planets orbiting them. While direct imaging remains challenging for all but the largest, brightest, and most distant planets, it provides information unavailable through other methods, including details about a planet's surface features and cloud patterns. But even with these advanced tools, studying exoplanets remains challenging. Most are detected indirectly. We don't actually see them as distinct objects, but rather infer their presence from their effects on their parent stars. This means our understanding is built on models and simulations rather than direct observation. When astronomers announce the discovery of a lava world or a glass rain planet, they're describing the most likely scenario given the data available, always acknowledging that future observations might refine or even dramatically change our understanding. The theoretical basis for interpreting these observations draws from multiple scientific disciplines. Atmospheric physics helps scientists understand how different gases behave under various temperature and pressure conditions. Geophysics provides insights into how a planet's interior structure influences its surface conditions. Chemistry reveals how different elements and compounds interact in extreme environments. Fluid dynamics explains the behavior of winds, currents, and weather patterns on alien worlds. By combining these different perspectives, scientists construct comprehensive models of exoplanet conditions. Computer simulations play a crucial role in this process. Modern supercomputers can model the complex interactions of atmosphere, surface, and interior over a planet's entire history. They can simulate the chemistry of exotic atmospheres, the patterns of winds and currents, and even the formation and evolution of planetary systems as a whole. These simulations are constrained by observational data where available, but they also allow scientists to explore possibilities beyond what can be directly observed, generating testable predictions for future observations. As our understanding of exoplanets deepens, so too does our appreciation for their diversity. The traditional categories of terrestrial, rocky, and Jovian, gas giant planets have expanded to include super-Earths, rocky planets larger than Earth but smaller than Neptune, mini-Neptunes, gas-enveloped worlds smaller than Neptune, hot Jupiters, Jupiter-sized planets orbiting extremely close to their stars, and even rogue planets drifting through interstellar space without a parent star. Each category includes worlds with unique and often extreme conditions. Can life exist on such extreme planets? This question drives much of modern exoplanet research. Life as we know it requires liquid water, stable temperatures, and protection from radiation, conditions that seem impossible on many of these nightmare worlds. Yet life on Earth has been found thriving in volcanic vents where temperatures exceed 120 degrees Celsius, in Antarctic ice at -60 degrees Celsius, and even in radioactive environments that would kill humans within minutes. Extremophiles, organisms adapted to extreme conditions, continuously expand our understanding of life's resilience. The study of extremophiles on Earth informs our search for potential life elsewhere. Microorganisms called thermophiles thrive in hot springs and deep-sea hydrothermal vents at temperatures that would cook ordinary cells. Psychrophiles survive in permanent ice, metabolizing at temperatures close to freezing. Barophiles function under crushing pressures in the deepest ocean trenches. Acidophiles prosper in highly acidic environments like the Rio Tinto in Spain, while alkaliphiles adapt to caustic, high pH conditions. Radio-resistant organisms like Deinococcus radiodurans can withstand radiation levels 1,000 times what would kill a human. These extraordinary adaptations suggest that life, once established, can evolve to survive in conditions far more extreme than those in which it originally emerged. Some scientists speculate that life could evolve using different biochemistries, perhaps silicon instead of carbon, or ammonia instead of water. Organisms might theoretically evolve to withstand radiation levels thousands of times what humans could survive, or develop biological antifreeze to function in temperatures hundreds of degrees below freezing. Perhaps life could even harness the energy of molten metals, or utilize extreme pressure as part of its metabolic processes. While most of these hellish worlds are likely sterile, the universe's vastness suggests that life might find a way to adapt even in places we consider unimaginable. The field of astrobiology, the study of life in the universe, grapples with these possibilities. Researchers in this interdisciplinary field combine insights from biology, chemistry, geology, astronomy, and physics to understand the potential for life beyond Earth. They consider not just where life might exist now, but how it might originate and evolve under different conditions. Could life begin in the hydrocarbon lakes of a world like Saturn's moon Titan? Could it evolve in the subsurface oceans of icy moons like Europa and Enceladus? Could it even adapt to the harsh conditions of Venus's cloud layers, where temperatures and pressures are less extreme than at the surface? The search for habitable, or at least potentially habitable, worlds continues alongside our investigation of these cosmic nightmares. Astronomers have identified dozens of exoplanets in their stars habitable zones, where temperatures might permit liquid water. Some of these planets are similar in size to Earth, raising hopes that they might harbor conditions friendly to life. The reality, however, is that habitability depends on many factors beyond mere distance from a star. Atmospheric composition, magnetic field strength, planetary mass, geological activity, and many other variables determine whether a world could support life as we know it. The extreme worlds we'll explore represent the opposite end of this spectrum, the most hostile environments ever discovered. They serve as cosmic laboratories where physics and chemistry operate at their limits. By studying these extremes, scientists gain insights into fundamental planetary processes. How do atmospheres form and evolve? What drives weather patterns on alien worlds? How do a planet's core, mantle, and crust interact over billions of years? The answers to these questions enhance our understanding not just of distant exoplanets, but of our own Earth as well. These nightmare planets also provide crucial context for Earth's place in the cosmos. Our home world exists in a relatively narrow band of conditions that permit liquid water, moderate temperatures, and a hospitable atmosphere. The more extreme planets we discover, the more we appreciate Earth's perfect balance. Not too close to the sun, not too far, not too large, not too small, with just the right atmospheric composition and just the right level of geological activity. Earth's conditions, it seems, are relatively rare in the universe, making our planet all the more precious. The discovery of these extreme worlds also challenges our understanding of planetary formation and evolution. Traditional models suggested that planets form in orderly systems, with rocky worlds close to their stars and gas giants farther out, much like our own solar system. But the exoplanet census reveals a far messier reality, with giant planets orbiting close to their stars, tiny worlds in distant orbits, and planets of all types packed into systems far more compact than our own. These observations have forced scientists to revise their theories, considering processes like planetary migration, where worlds form in one location and then move to another due to gravitational interactions. The conditions on these extreme planets often result from unique evolutionary histories. Some hot Jupiters, for instance, likely formed far from their stars and then migrated inward, their atmospheres and structures transforming as they entered increasingly hostile environments. Super-Earths may represent a class of planet that never had the chance to form in our solar system, their evolution shaped by forces and timescales different from those that governed Earth's development. By studying these diverse worlds, scientists piece together a more complete picture of how planetary systems form and change over billions of years. The philosophical implications of these discoveries are profound. For millennia, humans imagined other worlds as variants of Earth, perhaps with different landscapes or creatures, but fundamentally similar to our home. Modern astronomy has shattered this anthropocentric view, revealing a universe filled with planets so alien that they stretch the very definition of what a world can be. This cosmic perspective humbles us, forcing us to reconsider our place in a universe far stranger and more diverse than our ancestors could have imagined. The cultural impact of exoplanet discoveries extends beyond scientific communities. These findings have influenced literature, film, art, and popular imagination, inspiring a new generation of science fiction that grapples with truly alien environments rather than simply transplanting Earth-like conditions to other worlds. Works like The Three-Body Problem by Liu Cixin or Children of Time by Adrian Tchaikovsky draw directly from our evolving understanding of extreme exoplanets, creating stories that reflect the universe's true diversity rather than anthropocentric fantasies. As we embark on this tour of nightmare worlds, we'll encounter planets where the laws of physics create conditions that seem impossible, yet are very real. From rains of molten glass to oceans of liquid metal, from clouds of vaporized rock to atmospheres thick enough to blur the line between gas and liquid, these phenomena exist on actual planets orbiting actual stars. They represent not the imagination of science fiction writers, but the observed reality of our universe. The psychological impact of these discoveries is significant as well. Humans evolved on Earth's surface, under one Earth gravity, breathing Earth's specific atmospheric mix, and experiencing Earth's particular range of temperatures. Our instincts, fears, and comforts are all calibrated to this environment. The extreme worlds we'll explore trigger deep discomfort precisely because they violate everything our evolutionary history has prepared us for. They are places where humans could never belong, alien in the truest sense of the word. Yet there's beauty in this cosmic hostility. The same forces that create these nightmare conditions also generate phenomena of extraordinary splendor. Imagine standing in an impossible protective suit on the night side of a tidally locked planet, watching clouds of vaporized iron blow in from the day side and condense into a rain of liquid metal, falling like shimmering silver through an alien sky. The universe's extremes create not just terror, but wonder. This tension between terror and wonder defines our relationship with cosmic extremes. The same planet that would kill a human visitor instantaneously might, viewed from a safe distance, present a spectacle of unparalleled beauty. The super-dense atmosphere that would crush a spacecraft might create optical effects that paint the sky in colors unseen on Earth. The scalding winds that would scour flesh from bone might sculpt cloud formations of breathtaking complexity. In these hostile worlds, we find both nightmare and marvel, often simultaneously. For future human space exploration, these extreme planets represent both challenge and opportunity. While direct human visitation to most of these worlds remains firmly in the realm of science fiction, robotic exploration may eventually be possible. Engineers are already developing technologies capable of surviving the crushing pressures of Venus's atmosphere or the radiation-blasted surface of Io. Future probes might drift through the cloud layers of gas giants, descend into the methane lakes of Titan, or sample the atmosphere of distant exoplanets. Each such mission would push the boundaries of human ingenuity and expand our understanding of the cosmic laboratory. As we take this journey together, we'll use the best available science to understand these worlds, while acknowledging the limitations of our knowledge. Many of the planets we'll discuss have been studied only indirectly, their conditions inferred rather than directly observed. Future observations may revise our understanding, perhaps making some worlds seem even more extreme, while revealing others to be less hostile than currently believed. This is the nature of science. Our knowledge grows and changes as our tools and techniques improve. The planets we'll explore represent the most extreme environments ever discovered, cosmic laboratories where physics and chemistry operate at their limits. From worlds with oceans of lava to planets continuously torn apart by gravitational forces, these places reveal the universe's capacity for both beauty and terror. They also highlight, through stark contrast, how precious and rare our own planet's gentle conditions truly are. So prepare yourself for a journey to the most inhospitable corners of our galaxy, a tour of cosmic horror that makes even the harshest environments on Earth seem like paradise by comparison. The universe is far stranger and more terrifying than we could have imagined, and these nightmare worlds are the proof. Let's start with a planet where it rains molten glass sideways. HD 189733b appears deceptively serene when viewed from a distance. This hot Jupiter exoplanet, discovered in 2005, orbits a star about 63 light-years from Earth in the constellation Vulpecula. Initial observations revealed a world with a striking deep blue color, reminiscent of Earth's oceans, creating a falsely comforting first impression. But this sapphire giant harbors conditions so extreme that it ranks among the most hostile environments ever discovered in the cosmos. The planet's beautiful azure hue doesn't come from water oceans, but from something far more sinister: silicate particles in its atmosphere. These tiny fragments of glass scatter blue light, creating the planet's distinctive color. But unlike Earth's peaceful blue skies, the atmosphere of HD 189733b is a maelstrom of violence, with winds exceeding 8,000 kilometers per hour, roughly 7 times the speed of sound on Earth and faster than any hurricane, tornado, or wind ever recorded on our planet. These supersonic winds don't merely howl across the planet's surface. They drive a weather phenomenon unlike anything in our solar system: horizontal glass rain. As the planet's atmospheric temperature varies between its day and night sides, silicate particles in the upper atmosphere condense into glass droplets. These aren't gentle raindrops, but microscopic daggers of razor-sharp glass, whipped sideways by the ferocious winds, creating a perpetual storm of flying shards that would flay human skin in seconds and shred even the most advanced spacecraft materials like tissue paper. The discovery of HD 189733 marked a significant moment in exoplanet astronomy. It was among the first exoplanets to have its atmosphere directly detected and studied in detail. The planet was identified using the transit method, where astronomers measure the tiny dip in starlight as the planet passes in front of its star. This discovery was made by a team led by François Bouchy using the LOD spectrograph on the 1.93-meter telescope at Observatoire de Haute-Provence in France. The initial detection revealed a massive planet approximately 1.14 times the radius of Jupiter, orbiting extremely close to its parent star. What made HD 189733b particularly valuable to astronomers was its large size relative to its star and its frequent transits, occurring every 2.2 Earth days. These characteristics made it an ideal candidate for follow-up studies using more advanced instruments. In the years since its discovery, this exoplanet has become one of the most intensively studied worlds outside our solar system, serving as a test case for new observational techniques and theoretical models of exoplanet atmospheres. The orbital dynamics of HD 189733b create conditions perfect for this nightmare weather. The planet orbits extremely close to its parent star, completing a full orbit in just 2.2 Earth days. This proximity means the planet is tidally locked, with one side perpetually facing its star while the other remains in darkness. The temperature on the day side reaches a blistering 1,200 degrees Celsius, hot enough to melt lead, zinc, and some alloys of steel. Meanwhile, the night side, while still scorching by Earth standards, may be hundreds of degrees cooler. This extreme temperature differential drives the planet's apocalyptic wind patterns. Hot air from the day side rushes toward the cooler night side, creating a permanent circumplanetary jet stream of unprecedented power. The planet's rapid rotation, it spins faster than Earth despite being 60% larger, further accelerates these winds through Coriolis forces, the same phenomenon that shapes hurricane rotation on Earth, but magnified to terrifying proportions. The parent star, HD 189733, is a K-type main sequence star, slightly cooler and smaller than our Sun. It's part of a binary system, paired with a red dwarf star, designated HD 189733b, not to be confused with the planet HD 189733b. This stellar companion orbits at a distance of about 216 astronomical units, far enough that it likely has minimal influence on the planet's environment, but close enough to create a spectacular sight in the planet's sky, appearing as a bright reddish star. The planet itself is classified as a hot Jupiter, a gas giant similar in size and composition to Jupiter, but orbiting extremely close to its star, with a mass about 1.13 times that of Jupiter and orbiting at just 1/30th the distance between Earth and the Sun. HD 189733b experiences stellar heating over 4,000 times more intense than what Jupiter receives from our Sun. This proximity to its star means the planet is almost certainly tidally locked, with the same hemisphere always facing the star, similar to how the same side of the Moon always faces Earth. The composition of HD 189733b's atmosphere makes these conditions even more perilous. Spectroscopic observations have detected water vapor, carbon monoxide, and possibly methane and carbon dioxide. But it's the presence of magnesium silicate, essentially a form of glass, that creates the planet's most distinctive and lethal feature. At the scorching temperatures of the day side, these silicates vaporize into the atmosphere. As they're carried by the relentless winds to the relatively cooler night side, they condense into microscopic glass droplets, forming clouds and rain of molten glass that are then hurled sideways at supersonic speeds. This silicate rain cycle is continuous and planet-wide. Computer models suggest that the glass particles might be as small as dust or as large as sand grains. Either way, they create an environment where any unprotected surface would be sandblasted down to its molecular components within hours. Even materials designed to withstand the harshest conditions on Earth would quickly disintegrate under this relentless barrage. The detection of this silicate glass in HD 189733b's atmosphere was a triumph of modern astronomical techniques. Scientists used transmission spectroscopy, analyzing how the planet's atmosphere absorbs and filters starlight during transits, to identify specific wavelengths corresponding to silicate compounds. Further observations with infrared instruments confirmed the presence of these materials and helped astronomers understand their distribution and behavior in the planet's atmosphere. One of the most remarkable achievements in the study of this world came in 2007, when the Spitzer Space Telescope created the first ever temperature map of an exoplanet by measuring the infrared emissions from different parts of HD 189733b. This map confirmed the extreme temperature difference between the day and night sides and provided direct evidence for the powerful winds redistributing heat across the planet. Later observations using the Hubble Space Telescope added detail to this picture, detecting specific molecular signatures and variations in cloud coverage. The planet's extreme proximity to its star creates another peril: intense radiation. HD 189733b orbits a K-type star smaller and cooler than our Sun, but still powerful enough to bombard the planet with intense ultraviolet and X-ray radiation. The planet's outer atmosphere is constantly being heated and partially blown away by this stellar wind, creating a comet-like tail of evaporating atmospheric gases that stretches out behind it as it orbits. This atmospheric erosion, detected through ultraviolet observations with the Hubble Space Telescope, reveals another layer of extremity to this world. The planet is literally being boiled away by its star, losing an estimated 1,000 tons of material every second. While this might sound catastrophic, the planet is so massive that it would take trillions of years at this rate to completely evaporate, far longer than the star's lifetime. Nevertheless, this continuous atmospheric loss shapes the planet's composition and structure, potentially exposing deeper layers of its atmosphere over time. What would happen to a human unlucky enough to find themselves on this world? Death would be instantaneous and come from multiple directions simultaneously. Without a specialized pressure suit, the atmospheric pressure, estimated to be similar to standing under several kilometers of Earth's ocean, would crush a human body instantly. Even if protected from the pressure, the extreme heat would vaporize any exposed organic material within seconds. The glass rain would shred any conventional spacesuit materials, and the radiation levels would deliver lethal doses almost immediately. Even if we imagine an impossibly advanced protective suit that could somehow withstand these conditions, the experience of standing on HD 189733b would be utterly alien. The massive parent star would dominate the sky on the day side, appearing 7 times larger than our Sun appears from Earth. The light would be filtered through layers of exotic clouds, potentially creating otherworldly colors and atmospheric effects. The constant roar of supersonic winds would be deafening, though the density of the atmosphere might create acoustic properties unlike anything on Earth. On the night side, the sky would be illuminated by the glow of the superheated day side visible around the limb of the planet, creating a permanent sunset-like effect along the terminator, the boundary between day and night. The distant companion star would be visible as a bright red point, along with the stars of our galaxy appearing in unfamiliar configurations. The continuous rain of molten glass would create a perpetual hissing and tinkling as particles struck the ground and each other, a soundtrack to accompany the apocalyptic landscape. Even a hypothetical probe designed specifically for this environment would face almost insurmountable challenges. The extreme heat would make cooling systems essential, yet difficult to maintain. The glass rain would erode optical sensors, communications equipment, and protective coatings. The intense pressure would compress any hollow structures not reinforced to submarine standards. The radiation would interfere with electronics and degrade materials. Any mission to directly study HD 189733b would require technological advancements far beyond our current capabilities. Despite these challenges, astronomers have managed to study this world in remarkable detail, using space telescopes and ground-based observatories. The Hubble Space Telescope created a temperature map of the planet, confirming the extreme heat of its dayside. The Spitzer Space Telescope measured the planet's heat emissions, helping scientists understand its atmospheric circulation. Ground-based spectroscopic observations have revealed details about its atmospheric composition. Each new observation has only confirmed the planet's status as one of the most hostile environments known to science. Perhaps the most surprising discovery about HD 189733b came in 2008, when astronomers detected methane and water vapor in its atmosphere. These molecules are known as biomarkers because they're associated with life on Earth. However, on this scorching world, they're simply part of the complex atmospheric chemistry driven by extreme heat and pressure. Their presence demonstrates how careful scientists must be when searching for signs of life on distant worlds. What might appear as a biosignature in one context could be produced by entirely non-biological processes in another. The extreme weather on HD 189733b raises profound questions about atmospheric dynamics and climate systems. On Earth, our weather is driven by the interaction of solar heating, atmospheric composition, and planetary rotation. HD 189733b demonstrates how these same physical principles, operating under different conditions, can create weather systems of unimaginable violence. By studying such extreme cases, scientists gain insights into the fundamental physics governing all planetary atmospheres, including Earth's. The three-dimensional atmospheric models developed to understand HD 189733b have helped refine our knowledge of fluid dynamics, radiative transfer, and atmospheric chemistry. These models must account for phenomena rarely encountered on Earth, such as supersonic winds, partial ionization of gases, and exotic phase transitions between different states of matter. The computational techniques developed for studying this extreme exoplanet have applications in Earth climate science, improving our ability to model complex atmospheric processes on our own planet. HD 189733b challenges our understanding of planetary formation as well. Traditional models suggest that planets like this, hot Jupiters, shouldn't exist so close to their stars. They likely formed much farther out, where temperatures were cool enough for gases and ices to condense, and then migrated inward due to gravitational interactions with other planets or the protoplanetary disk. This migration would have transformed the planet, potentially stripping away its outer layers and leaving it with its current exotic composition. The study of HD 189733b and similar hot Jupiters has forced astronomers to revise their theories of how planetary systems form and evolve. Early models assumed that planets form and remain in relatively stable orbits, similar to what we see in our solar system. The discovery of hot Jupiters revealed that planetary migration, the movement of planets from their birth orbits to new positions, plays a much more significant role than previously thought. This insight has ripple effects for understanding all planetary systems, including the history of our own solar system. Some theoretical models suggest that HD 189733b may have a solid core made of rock and metal, similar to, but much larger than Earth's core. This core would be surrounded by a mantle of exotic materials, substances that are gases or liquids on Earth, but exist in strange states under the extreme pressures inside the planet. Above this would be the thick atmosphere, extending thousands of kilometers above the core, and gradually transitioning from supercompressed gases near the center to the more diffuse outer layers where the glass rain forms. The discovery of planets like HD 189733b has revolutionized our understanding of the diversity of worlds possible in the universe. Before exoplanet astronomy, scientists based their expectations on our own solar system, where the inner planets are small and rocky, while the outer planets are gas giants with relatively mild temperatures. HD 189733b and other hot Jupiters shattered this paradigm, revealing that planetary systems can form in configurations radically different from our own. This expanded view of what constitutes a normal planetary system has profound implications for estimating the frequency of Earth-like worlds in the galaxy. If our solar system's architecture is just one possibility among many, then the conditions that allowed Earth to form and remain habitable might be rarer than initially thought. Conversely, the diversity of planetary systems might create opportunities for habitability in configurations unlike our own, such as potentially habitable moons orbiting gas giants or planets in binary star systems. Could any form of life exist on such a world? By any conventional definition, HD 189733b is completely hostile to life as we understand it. No known organism could survive its extreme temperatures, pressures, and weather conditions. Even the most resilient extremophiles on Earth would find no safe haven on this glass rain world. However, some scientists speculate about the possibility of exotic life forms in the upper atmospheres of hot Jupiters, where temperatures might be more moderate and complex chemistry could potentially occur. While highly speculative, such hypotheses remind us that life might find ways to adapt to conditions we consider impossible. In the uppermost layers of HD 189733b's atmosphere, temperatures may drop to only a few hundred degrees Celsius, and pressures might approach those found in Earth's deep oceans. Some researchers have suggested that hypothetical organisms based on silicon rather than carbon, using chemical processes vastly different from Earth life, might conceivably survive in such environments. These organisms would need to be perpetually airborne, perhaps using the planet's powerful updrafts to stay aloft, and would require metabolic processes efficient enough to repair the continuous damage from radiation and heat. While such speculation remains firmly in the realm of science fiction, it highlights an important principle in astrobiology. We should be careful not to limit our search for life to environments that mimic Earth's conditions. Life on our planet has repeatedly demonstrated its ability to adapt to extremes that once seemed incompatible with biology. The study of worlds like HD 189733b, even if they themselves are sterile, expands our understanding of the parameters within which life might potentially exist. The existence of planets like HD 189733b also emphasizes how precious and rare Earth's conditions are. Our planet exists in a narrow, habitable zone, with temperatures allowing liquid water, a protective but not crushing atmosphere, and a stable orbit that creates predictable seasons rather than extreme temperature variations. The more we learn about worlds like HD 189733b, the more we appreciate the delicate balance that makes Earth habitable. This perspective has implications for how we value and protect our own planet. Understanding the cosmic extremes represented by HD 189733b throws into sharp relief the remarkably favorable conditions we enjoy on Earth. Our planet's atmosphere, rather than harboring supersonic glass storms, provides the perfect pressure for liquid water and shields us from harmful radiation. Our moderate temperatures allow for complex carbon-based life rather than vaporizing organic molecules. Our gentle winds distribute heat and moisture rather than scouring the surface with hypersonic particles. As astronomical instruments continue to improve, we'll learn even more about this sapphire nightmare world. The James Webb Space Telescope has the capability to study the planet's atmosphere in unprecedented detail, potentially revealing new components and providing a more precise understanding of its temperature structure. Future ground-based telescopes with advanced adaptive optics might even be able to directly image features in the planet's atmosphere, giving us our first weather map of this distant world. Recent observations have already revealed surprising complexities in HD 189733b's atmosphere. Studies of the planet during its transit have detected variations in atmospheric composition and temperature that suggest the presence of massive storm systems, perhaps analogous to, but far more powerful than Jupiter's Great Red Spot. Some observations hint at stratified cloud layers with different compositions at different altitudes, creating a complex vertical structure that current models are still struggling to fully explain. The study of HD 189733b serves as a reminder of both the limitations and the remarkable capabilities of modern astronomy. We can detect and characterize a planet orbiting a star 63 light-years away, a distance so vast that light itself, traveling at 300,000 kilometers per second, takes 63 years to cross it. Yet despite this vast separation, we can determine the planet's size, mass, orbital period, temperature, and even aspects of its atmospheric composition. This achievement represents one of humanity's greatest scientific triumphs. For now, HD 189733b stands as a testament to the extreme conditions possible on alien worlds, a place where the beautiful blue color that reminds us of Earth's peaceful oceans actually signals one of the most violent and hostile environments ever discovered. It's a world of contradictions, visually stunning, yet utterly deadly, familiar in its basic physical principles, yet alien in their manifestations, scientifically fascinating, yet existentially terrifying. As we leave this world of supersonic glass rain and journey deeper into the cosmos, we'll encounter planets with conditions that seem even more impossible. Yet each of these cosmic nightmares operates according to the same laws of physics that govern our own world. A humbling reminder that the universe's horrors emerge not from breaking natural laws, but from pushing them to their extremes. Now, imagine a planet where the surface is literally made of lava. K2141b represents a terrifying vision of planetary hell, a world where the concept of ground becomes meaningless when the surface itself is a churning ocean of molten rock. This exoplanet, discovered in 2018 as part of NASA's extended Kepler mission, orbits a bright orange dwarf star, approximately 200 light-years from Earth, while HD 189733b assaults visitors with glass rain from above. K2141b would dissolve them from below in its planet-wide magma sea. Unlike the gas giant we just explored, K2141b belongs to a class of planets called super-Earths, worlds larger than our home planet, but significantly smaller than Neptune. With a radius about 1.5 times that of Earth and a mass around 5 times greater, this exoplanet has enough gravitational pull to maintain a thin rocky crust, but that's where any similarity to Earth ends. K2141b orbits so close to its star that its surface temperature on the day side reaches an almost incomprehensible 3,000 degrees Celsius, hot enough to vaporize rock itself. The planet's proximity to its star creates perhaps its most dramatic feature, a vast lava ocean covering a significant portion of its surface. This isn't a localized feature like Earth's comparatively tiny volcanic regions, but an entire hemisphere where rock exists in liquid form. The day side of K2141b faces such extreme stellar heating that silicate rocks, the same materials that make up most of Earth's crust, melt into a magma ocean hundreds of kilometers deep. The surface glows white hot, radiating in both visible light and intense infrared, creating a hellscape that defies human comprehension. K2141b's orbit places it extraordinarily close to its parent star, completing a full circuit in just 6.7 hours. For perspective, Mercury, the closest planet to our Sun, takes 88 days to complete an orbit. This extreme proximity means K2141b is tidally locked, with one hemisphere permanently facing its star, while the other remains in perpetual darkness. This creates one of the most extreme temperature gradients ever observed on a planetary body, from 3,000 degrees Celsius on the day side to as low as -200 degrees Celsius on the furthest parts of the night side. This temperature differential drives a unique and terrifying weather cycle, unlike anything in our solar system. On the day side, the extreme heat doesn't just melt rock, it vaporizes it. Silicate compounds that form solid rock on Earth are heated to such extremes that they become a gaseous rock vapor, creating a thin but significant atmosphere of vaporized rock that surrounds the planet. This atmosphere, composed primarily of sodium, silicon monoxide, and silicon dioxide, reaches temperatures where the very concept of gas starts to blur with plasma, the fourth state of matter where atoms become ionized. As this superheated rock vapor rises from the magma ocean, it's caught in atmospheric circulation patterns driven by the temperature difference between day and night sides. Supersonic winds exceeding 5,000 kilometers per hour carry the vaporized rock toward the cooler night side. There, away from the star's relentless heat, the rock vapor begins to cool and condense, forming clouds not of water droplets, but of liquid rock, a molten rain of the same materials that make up Earth's mountains. As this rock rain falls through the increasingly cold atmosphere of the night side, it eventually solidifies, creating a precipitation of solid rock pebbles and dust. This extraordinary weather pattern, from liquid to gas to liquid to solid, creates a continuous cycle of rock material flowing from dayside to nightside in the atmosphere, and then flowing back to the dayside along the surface as the solid deposits gradually migrate due to the planet's rotation and gravitational effects. Computer models suggest that winds on K2141b may be permanently supersonic across much of the planet, breaking the sound barrier as they race from the superheated dayside to the freezing nightside. These winds don't just carry vaporized rock, they sculpt the very surface of the planet, eroding any solid features on the night side and redistributing materials across the globe. The sound of these winds, if one could somehow survive to hear them, would be a continuous, deafening roar, punctuated by the hiss and crack of molten rock cooling and solidifying. The discovery of K2141b came through NASA's K2 mission, an extended phase of the Kepler Space Telescope's operation after the failure of two of its reaction wheels. Despite this technical limitation, the repurposed mission continued to find exoplanets by detecting the tiny dips in starlight as planets transit across their stars. Following its initial detection, K2141b was confirmed through ground-based observations, including precise measurements of its mass using the radial velocity method, which detects the slight wobble the planet induces in its parent star. What makes K2141b particularly valuable to astronomers is that it orbits a relatively bright star, making detailed follow-up observations easier than for many other exoplanets. This brightness allowed scientists to gather enough data to develop sophisticated models of the planet's atmosphere and surface conditions, revealing the extraordinary rock cycle that makes this world unique among known exoplanets. The surface of K2141b likely contains a variety of exotic substances rarely seen on Earth except in laboratory conditions or extreme volcanic environments. The magma ocean probably contains high concentrations of silicon, oxygen, aluminum, iron, calcium, and magnesium, the primary elements that make up Earth's crust, but heated to such extremes that they form unusual compounds. Near the edge of the magma ocean where day meets night, strange mineralogical borderlands might exist, with semi-solid lakes of materials that would be completely solid rock on Earth. The night side of K2141b presents a different kind of extreme environment. Without the direct heating of the star, temperatures plummet to levels comparable to the outer solar system. This creates a frozen landscape, but not of water ice as on Earth's poles. Instead, the surface might consist of exotic forms of solidified silicon compounds, metallic precipitates, and unusual mineral formations created by the rapid cooling of materials that were completely vaporized just hours earlier on the day side. The boundary between the day and night sides, known as the terminator, would be perhaps the most dynamic and violent region of the planet. Here, the temperature gradient would be at its steepest, with temperatures potentially dropping by hundreds of degrees over just a few kilometers. Rivers of lava might flow from the dayside into the night, gradually cooling and solidifying, but continuously replenished by the endless supply of molten material from behind. The terminator might feature mountainous ridges formed by the continuous deposit of solidifying materials, only to be eroded by the supersonic winds carrying more molten debris. Why does K2141b never cool down, despite half the planet being in perpetual night? The answer lies in its extreme proximity to its star and its rapid orbit. The dayside receives such intense stellar radiation that the rock vaporization cycle is continuously powered, maintaining the magma ocean even as heat is transported to the night side. Additionally, the planet likely experiences intense tidal heating, frictional heat generated within its interior due to the gravitational pull of its star. This combination of external and internal heating sources maintains the extreme temperature gradient and drives the continuous rock cycle. The gravitational forces experienced on K2141b would be approximately 5 times stronger than on Earth due to the planet's greater mass and density. This increased gravity would compress the planet's atmosphere, keeping it relatively thin despite the continuous vaporization of surface materials. It would also affect the flow of molten rock, potentially creating unique fluid dynamics not seen in Earth's comparatively small lava flows. Any solid structures that might momentarily form in the boundary regions between day and night would be under enormous stress, likely fracturing and crumbling under their own enhanced weight. What would happen to a human unfortunate enough to visit this lava world? Death would be instantaneous and total. On the day side, the temperature exceeds that of cremation ovens by a factor of 3. A human body would not simply burn, it would vaporize, its constituent elements joining the atmosphere of rock vapor circulating around the planet. Even with theoretical heat shielding thousands of times more effective than anything currently available, no physical structure could maintain integrity in such an environment. On the night side, conditions are no less lethal, though death would come differently. The extreme cold, approaching that of liquid nitrogen, would freeze organic tissue instantly. The atmosphere, a toxic mix of vaporized rock compounds, gradually cooling and condensing, would be unbreathable. The rain of molten rock droplets solidifying into stone would hammer down like artillery. Even in the theoretical twilight zone between hemispheres, the combination of extreme temperature gradients, toxic atmosphere, and continuous bombardment by rock precipitation would ensure no survival. Could anything survive on K2141b? By any standard definition of life as we know it, the answer is an emphatic no. The temperature extremes far exceed the limits of even the most resilient extremophiles on Earth. The chemical environment would destroy organic molecules. The radiation levels from both the nearby star and the glowing hot surface would shred DNA, or any similar information-carrying molecule. Even theoretical silicon-based life forms, sometimes proposed as alternatives to carbon-based life, would find no stable environment on a world where silicon itself constantly cycles between solid, liquid, and gaseous states. Yet K2141b provides valuable insights into planetary processes that do operate on Earth, albeit at much less extreme scales. The rock cycle on Earth, where rocks form, erode, melt, and reform over geological time, takes millions of years to complete. On K2141b, a similar cycle occurs in hours or days. By studying this accelerated process, scientists gain new perspectives on geological phenomena that shape our own world, from volcanic eruptions to mineral formation under extreme conditions. The discovery of planets like K2141b has forced scientists to expand their understanding of what constitutes a habitable zone around stars. Traditional definitions focus on the distance from a star where water can exist as a liquid on a planet's surface, but K2141b demonstrates that planets can maintain dynamic, active surfaces even at distances where traditional models would predict completely static, dead worlds. This insight has applications for understanding potentially habitable worlds in other star systems. where conditions might allow for liquid water even on planets that don't fit neatly into conventional habitable zone calculations. K2141b also provides a laboratory for studying exotic states of matter. Under the extreme conditions found on this world, familiar materials behave in unfamiliar ways. Rocks don't just melt, they vaporize and then recondense in cycles driven by temperature and pressure gradients. These processes can inform laboratory experiments on Earth, attempting to create new materials or understand the behavior of matter under extreme conditions relevant to industrial applications. From an astronomical perspective, K2141b represents an endpoint in planetary evolution. It likely formed farther from its star and then migrated inward, perhaps due to gravitational interactions with other planets or drag from the protoplanetary disk. As it spiraled closer to its star, any volatiles like water or carbon compounds would have been baked away, leaving only refractory materials like silicates and metals. Its current state, locked in an eternal cycle of melting, vaporization, and resolidification, represents a type of planetary existence completely alien to anything in our solar system. The parent star of K2141b, a K-type orange dwarf, is smaller and cooler than our Sun, but still hot enough to create the extreme conditions we've described when a planet orbits as closely as K2141b does. K-type stars are of particular interest to astronomers because they live longer than Sun-like stars while providing more stable environments than the even smaller M-type red dwarfs. Under different circumstances, if K2141b orbited much farther from its star, the system might have been considered potentially habitable. Instead, it provides a case study in how proximity to a star can create extreme conditions that render a planet completely hostile to life. Recent observations of K2141b have allowed astronomers to refine their models of its unique rock cycle. By studying the planet during different phases of its orbit, scientists can observe how temperatures and atmospheric compositions vary, confirming theoretical predictions about the movement of vaporized rock between the day and night sides. These observations have revealed that the rock cycle is even more efficient than initially thought, with supersonic winds redistributing heat and materials across the planet at rates faster than early models predicted. The study of K2141b connects to broader questions about planetary formation and evolution. How common are such extreme worlds in the galaxy? Do most planetary systems contain planets that have migrated to orbits close enough to create lava worlds? How do these planets evolve over billions of years? Will K2141b eventually lose its entire atmosphere to space, leaving behind a barren, airless rock? Or might it spiral even closer to its star, eventually being torn apart by gravitational forces? These questions drive continuing observations and theoretical work. As with HD 189733b, the James Webb Space Telescope offers new opportunities for studying K2141b in unprecedented detail. Its infrared capabilities are ideally suited for analyzing the thermal emissions from this superheated world, potentially mapping temperature variations across different regions of the planet with greater precision than ever before. Such observations could reveal new complexities in the rock cycle and atmospheric circulation patterns that current models have only begun to capture. K2141b stands as a monument to the extremes of planetary evolution, a world transformed by its proximity to its star into a perpetual cycle of fire, vapor, and stone. It reminds us that planets are not static objects, but dynamic systems shaped by the continuous interaction of stellar radiation, gravity, and their own internal processes. In its endless cycle of melting and freezing, vaporizing and condensing, K2141b represents both the destructive and creative powers of the cosmos, forces that, in more moderate forms, shaped our own world into a haven for life. But even K2141b's molten surface pales in comparison to our next destination, a world where the very clouds are made not of water, not of sulfuric acid, not even of vaporized rock, but of something even more extreme. Iron heated to its melting point, falling as metallic rain through an atmosphere hot enough to melt steel. WASP 76b takes planetary extremes to a whole new level of nightmarish conditions. This massive gas giant, located about 640 light-years from Earth in the constellation Pisces, presents us with a weather forecast beyond imagination, cloudy with a chance of molten iron rain. While K2141b featured vaporized rock, WASP 76b goes a step further. Here, it's actual metal that falls from the sky. Discovered in 2013 as part of the Wide-Angle Search for Planets (WASP) program, this exoplanet immediately captured astronomers' attention due to its bizarre characteristics. WASP 76b is a type of planet we call an ultra-hot Jupiter, a gas giant similar in size to Jupiter, but orbiting extraordinarily close to its parent star. With a mass approximately 90% that of Jupiter, but nearly twice the diameter, WASP 76b is what astronomers call inflated, puffed up by the intense heat from its nearby star. And intense is perhaps an understatement. WASP 76b orbits its star at a distance of just 3 million kilometers, about 50 times closer than Earth orbits the Sun. At this proximity, the planet completes a full orbit in just 1.8 Earth days and is tidally locked, with one side permanently facing the scorching stellar surface. This creates temperature conditions more extreme than anything in our solar system. The day side of WASP 76b reaches temperatures of approximately 2,400 degrees Celsius, hot enough to vaporize many metals, including iron. For perspective, this temperature exceeds the melting point of most rocks and is hot enough to melt steel beams. The planet's atmosphere on this hemisphere is a chaotic mix of vaporized elements that would be solid on Earth, creating a gaseous soup of metals and minerals continuously heated by the nearby star. What makes WASP 76b truly extraordinary is the temperature contrast between its hemispheres. While the day side roasts at temperatures comparable to some stars, the night side, while still extremely hot by Earth standards, is several hundred degrees cooler. This temperature differential creates the conditions for one of the most exotic weather phenomena ever discovered: iron rain. Here's how this incredible process works. On the scorching day side, temperatures are high enough that iron, which makes up a significant portion of the planet's composition, exists as a gas vaporized by the extreme heat. This iron vapor gets caught in powerful atmospheric currents that carry it toward the planet's night side. As the iron-laden winds cross the terminator, the boundary between day and night, they encounter relatively cooler temperatures. There, the gaseous iron condenses into liquid droplets, forming clouds of molten metal that then precipitate as iron rain. This is not a gentle patter of rainfall as we know it on Earth. The iron droplets would be extraordinarily hot, around 1,500 degrees Celsius, and would fall through an atmosphere still hot enough to melt most metals. The drops would be significantly heavier than water raindrops on Earth, and would fall as a continuous metallic downpour across vast regions of the planet's night side. Imagine standing in an impossible heat-resistant suit beneath a shower of liquid metal droplets, each one hot enough to instantly vaporize organic material and heavy enough to carry devastating kinetic energy. The evidence for this remarkable phenomenon was discovered in 2020 by researchers using the ESPRESSO instrument on the European Southern Observatory's Very Large Telescope in Chile. By analyzing the light passing through the planet's atmosphere during its transit across its star, scientists detected a curious anomaly. The signature of iron vapor was present on the day side, but mysteriously absent on the night side. This observation is best explained by the iron rain mechanism. The iron doesn't disappear, it simply changes state from gas to liquid as it crosses to the cooler hemisphere. The winds driving this metal weather system are nothing short of spectacular. Computer models suggest that WASP 76b experiences wind speeds exceeding 10,000 kilometers per hour, over 8 times faster than the speed of sound on Earth. These hypersonic winds are propelled by the enormous temperature differential between hemispheres and are powerful enough to carry vaporized metals across thousands of kilometers before they condense into their liquid form. WASP 76b's parent star, WASP-76, is an F-type star larger and hotter than our Sun. This increased stellar energy output, combined with the planet's extremely close orbit, creates the perfect conditions for maintaining the iron rain cycle. The star continuously pumps enough energy into the day side to keep metals vaporized, while the night side remains just cool enough to allow condensation. The atmospheric composition of WASP-76b is primarily hydrogen and helium, similar to Jupiter, but with a much higher metal content in its atmosphere due to the extreme heat vaporizing elements that would normally remain in the planet's core or mantle. Spectroscopic observations have detected not just iron, but also other metals like magnesium, chromium, and titanium in gaseous form. These metals contribute to complex atmospheric chemistry, unlike anything in our solar system. The pressure conditions across WASP-76b's atmosphere create additional extremes. Near the boundary between day and night, where temperatures change most dramatically, pressure gradients drive the powerful winds that transport vaporized iron. Deeper in the atmosphere, pressures increase to levels that would crush any spacecraft from Earth. At sufficient depth, the hydrogen in the atmosphere is compressed so intensely that it transitions into a metallic state, a form of matter that behaves both as a liquid and a conductor, similar to the deep interior of Jupiter. What would it be like to descend through the atmosphere of WASP-76b? Starting from space, you would first pass through the uppermost layers of the atmosphere, already hot enough to melt lead and zinc. As you descended deeper, temperatures and pressures would increase dramatically. If approaching from the day side, you would pass through gaseous metal clouds, where elements that are solid on Earth exist as vapor. The atmosphere would glow with the heat, creating an eerie illumination even without direct starlight. Crossing toward the night side, you would encounter the iron condensation front, a region of incredible turbulence where liquid iron begins to form in the cooling atmosphere. Here, the first droplets of molten iron would appear, initially as a fine metallic mist that gradually coalesces into larger drops. Continuing into the night side, you would experience the full iron rainstorm, a continuous downpour of molten metal falling through the hot, dense atmosphere. Could anything survive on such a world? The answer, by any conventional definition of life, is no. The temperatures on WASP-76b far exceed the upper limits for any known biological processes. Even the most heat-tolerant organisms on Earth cannot survive above 120 degrees Celsius, and most complex molecules necessary for life break down at much lower temperatures. The presence of liquid iron rain would instantly destroy any organic compounds, and the intense radiation from both the nearby star and the planet's own thermal emissions would break apart any complex molecules. Even if we imagine some form of exotic life completely unlike anything on Earth, perhaps based on high-temperature plasma processes rather than carbon chemistry, the violent, chaotic conditions of WASP-76b's atmosphere would present overwhelming challenges. The supersonic winds, extreme temperature gradients, and continuous metallic precipitation create an environment where stable, self-organizing systems, a fundamental requirement for anything we might recognize as life, would struggle to form and persist. From a scientific perspective, WASP-76b provides an extraordinary natural laboratory for studying extreme planetary physics and atmospheric dynamics. The iron rain cycle observed here may represent just one example of exotic meteorological processes that occur on ultra-hot gas giants throughout the galaxy. By understanding the mechanisms driving this cycle, scientists gain insights into fundamental questions about how atmospheres work under extreme conditions. The study of planets like WASP-76b has practical applications for our understanding of material science as well. The behavior of metals and other elements under the extreme temperatures and pressures found in this atmosphere is difficult to replicate in laboratories on Earth. Observations of these natural extreme environments provide valuable data for refining models of how materials behave under conditions relevant to industrial processes, from metallurgy to high-temperature engineering. WASP-76b also offers insights into the evolution of planetary systems. Its current state, an ultra-hot Jupiter orbiting extremely close to its star, is likely not how it originally formed. Gas giants are believed to form farther from their stars, where temperatures are cool enough for ices to condense and accumulate into planetary cores. WASP 76b probably migrated inward through gravitational interactions with other planets, or with the protoplanetary disk from which it formed. This migration dramatically transformed the planet from what may have been a more temperate gas giant similar to Jupiter into the extreme world we observe today. The fate of WASP 76b over astronomical time raises intriguing questions. Will it maintain its current orbit indefinitely, continuously cycling iron between gaseous and liquid states? Or might it spiral even closer to its star, eventually being torn apart by gravitational forces? Could it gradually lose its atmosphere to space due to the intense stellar radiation, leaving behind a smaller, denser core? The answers to these questions have implications for understanding the life cycles of the many hot Jupiters that have been discovered throughout our galaxy. Recent observations with advanced instruments continue to reveal new complexities in WASP 76b's atmosphere. Beyond the iron rain, scientists have detected evidence of chemical segregation between the day and night sides, with different elements and compounds predominating in different hemispheres. This chemical asymmetry adds another layer to the planet's alien nature and suggests that the iron rain may be just one of several exotic phase transitions occurring in this extreme environment. One particularly fascinating discovery is the potential for clouds composed not just of iron, but of other exotic substances. Titanium oxide, which is found in sunscreens on Earth, may form high-altitude clouds on the day side before dissociating in the extreme heat. Silicate clouds, essentially vaporized rock condensing into liquid droplets, might exist alongside the iron clouds, creating complex layered weather systems. Some models even suggest the possibility of aluminum oxide rain on parts of the night side, adding to the metal precipitation. The boundary region between day and night, the terminator line, is potentially the most dynamic and violent part of WASP 76b. Here, the temperature drops by hundreds of degrees over relatively short distances, creating intense atmospheric turbulence. The iron rain likely begins forming in this region, with the first metallic condensation occurring in the upper atmosphere and growing as the air continues to cool while moving nightward. This transition zone might feature some of the most violent storms in the planet's atmosphere, with upwelling hot air from the dayside colliding with metal-laden downdrafts from the cooling regions. WASP 76b challenges our understanding of what constitutes a normal planet. Before the discovery of exoplanets, our models of planetary formation and evolution were based entirely on our solar system, where gas giants orbit at comfortable distances from the Sun and experience relatively moderate temperatures. The existence of ultra-hot Jupiters like WASP 76b, with their exotic atmospheric chemistry and extreme weather, has forced a complete rethinking of planetary science. They represent an entirely different evolutionary path for gas giants, one that results in conditions so alien they seem more like something from science fiction than astronomical reality. Looking toward future research, WASP 76b remains a prime target for observations with next-generation instruments. The James Webb Space Telescope, with its unprecedented infrared capabilities, can provide even more detailed analysis of the planet's atmospheric composition and temperature structure. Future ground-based extremely large telescopes may eventually be able to directly image features in the planet's atmosphere, potentially giving us our first visual glimpse of the iron clouds and other exotic phenomena. The existence of planets like WASP 76b reminds us of the incredible diversity of worlds in our galaxy. For every Earth-like planet in a comfortable orbit around a Sun-like star, there may be dozens or hundreds of extreme worlds where the laws of physics create conditions beyond our everyday experience. These cosmic laboratories, where iron falls as rain, where winds exceed the speed of sound, where temperatures rival those of stars, expand our understanding of what's possible in the universe. As we contemplate the iron rain of WASP 76b, we're reminded that even the most extreme environments in our galaxy still operate according to the same fundamental laws of physics that govern our own world. The same principles of thermodynamics that create gentle water rain on Earth create molten metal rain on this distant planet. The same gravitational forces that hold Earth in orbit around the Sun keep WASP 76b locked in its cosmic dance with its star. The universe, for all its alien wonders, remains consistent in its underlying rules, a fact that makes these extreme worlds not just horrifying, but scientifically comprehensible. As we leave this world of molten metal weather and continue our tour of cosmic nightmares, we'll next visit a planet much closer to home, yet in many ways just as hostile to human life. Let's turn our attention to our sister planet, Venus, which despite its proximity has conditions that rival the exoplanets we've explored in their lethality. Now, let's move to a world where the air itself is poison. Venus, our closest planetary neighbor, presents perhaps the most disturbing cosmic horror of all, not because its conditions are the most extreme we've encountered, but because this world serves as a dark mirror to our own. Often called Earth's sister planet, or twin, due to its similar size and composition, Venus instead evolved into a vision of planetary hell that haunts astronomers and planetary scientists as a stark warning of what could have been, or what might still be, Earth's fate. Orbiting just 108 million kilometers from the Sun, roughly 2/3 of Earth's distance, Venus receives almost twice the solar radiation that Earth does. But this proximity alone doesn't explain Venus's extreme conditions. After all, Mercury orbits even closer to the Sun, yet lacks Venus's infernal environment. What transformed this Earth-sized world into one of the most hostile places in the solar system was a runaway greenhouse effect that serves as an apocalyptic warning for our own climate crisis. Venus's atmosphere is a suffocating blanket 90 times thicker than Earth's, creating a surface pressure equivalent to being almost 1 kilometer deep in Earth's oceans. This crushing atmosphere is composed of 96% carbon dioxide, the same greenhouse gas that concerns climate scientists on Earth, but present in vastly greater quantities. The extreme pressure alone would kill an unprotected human instantly, compressing the body until it collapsed. But pressure is just the beginning of Venus's horrors. The planet's thick carbon dioxide atmosphere traps heat with devastating efficiency, creating a runaway greenhouse effect that has raised surface temperatures to approximately 465 degrees Celsius, hot enough to melt lead, zinc, and several other metals. This temperature is remarkably consistent across the entire planet, with little variation between day and night or between equator and poles, creating a world where there is no escape from the heat. The clouds of Venus add another layer of terror to this already nightmarish world. Unlike Earth's life-giving water clouds, Venus is shrouded in thick, yellowish clouds of sulfuric acid, one of the most corrosive substances known. These acid clouds completely encircle the planet between 40 and 50 kilometers above the surface, reflecting most incoming sunlight, which is why Venus appears so bright from Earth, while helping to trap heat below. Any unprotected human tissue exposed to these clouds would be chemically burned within seconds. Venus's combination of heat, pressure, and corrosive chemistry creates an environment so hostile that it has destroyed every spacecraft that has landed on its surface. The Soviet Venera probes of the 1970s and 1980s, the only human-made objects ever to return images from Venus's surface, survived for merely minutes to hours before succumbing to the extreme conditions. Their images revealed a desolate landscape of fractured plains and weathered rocks beneath an eerie, sulfur-tinted sky. A truly alien vista despite being our closest planetary neighbor. Perhaps most unsettling about Venus is how similar it may have once been to Earth. Geological evidence suggests that Venus might have had oceans of liquid water for billions of years during its early history. The planet's size, density, and composition closely mirror Earth's, suggesting that the two worlds started on similar evolutionary paths. Some scientists even speculate that ancient Venus might have been habitable, potentially supporting primitive life forms during its watery phase. What happened to transform this potentially Earth-like world into a planetary inferno? The most widely accepted theory involves a catastrophic climate feedback loop. As Venus receives more solar energy than Earth, its early oceans would have experienced more evaporation, increasing atmospheric water vapor, itself a potent greenhouse gas. This initial warming led to more evaporation, more water vapor, and even more warming. Eventually, the oceans completely evaporated, and water molecules in the upper atmosphere were broken apart by ultraviolet radiation, allowing the hydrogen to escape to space while the oxygen combined with other elements in the crust. Meanwhile, volcanic activity, which continues on Venus today, released carbon dioxide that accumulated in the atmosphere. On Earth, carbon dioxide is removed from the atmosphere through various processes, including dissolution in oceans and uptake by plants. With its oceans gone and no plant life to absorb carbon dioxide, Venus experienced a runaway buildup of this greenhouse gas, further intensifying the heating effect. Over time, surface temperatures rose to their current extreme levels, creating the hellish conditions we observe today. This history presents a chilling cautionary tale for Earth's climate future. While our planet's different distance from the Sun and other factors make a complete Venus-like transformation unlikely, the underlying physics of the greenhouse effect operates the same way on both worlds. Venus stands as an extreme example of how a planetary climate can fundamentally change when critical thresholds are crossed. A stark reminder of the importance of understanding and addressing Earth's own changing climate. The surface of Venus is a landscape of volcanic features, vast plains, and highland regions. Unlike Earth, Venus lacks plate tectonics, the movement of crustal plates that creates our planet's mountains, ocean trenches, and continents. Instead, Venus appears to release its internal heat through episodic, planet-wide volcanic resurfacing events. The most recent such event may have occurred as recently as 500 million years ago, explaining why Venus has relatively few impact craters compared to other solar system bodies. Most were wiped away during this global volcanic upheaval. The Venusian surface is dotted with distinctive volcanic formations. Shield volcanoes similar to Hawaii's Mauna Loa, but vastly larger, rise from the plains. Unique pancake domes, formed by thick, viscous lava, create circular plateaus hundreds of kilometers across. Perhaps most unusual are the coronae, concentric rings of fractures created when magma beneath the surface pushes the crust upward and then subsides, leaving circular scars hundreds of kilometers in diameter. These features paint a picture of a geologically active world, albeit one with a style of activity different from Earth's. Recent evidence suggests that Venus may still be volcanically active today. In 2020, scientists analyzing data from the European Space Agency's Venus Express mission identified hotspots that could indicate ongoing eruptions. The planet's thick clouds normally hide the surface from view, but infrared instruments can occasionally peer through specific wavelength windows to detect temperature variations below. The observed hotspots suggest that Venus isn't a geologically dead world, but continues to reshape its surface through volcanic processes. Venus rotates on its axis in a peculiar fashion. It spins backward compared to most other planets, with its sun rising in the west and setting in the east. Even more strangely, its rotation is extraordinarily slow, with a Venusian day lasting 243 Earth days, longer than the planet's year of 225 Earth days. This means that from any point on Venus's surface, the sun would rise, crawl slowly across the sky, and set over a period of approximately 120 Earth days. The causes of this bizarre rotation remain debated among planetary scientists. One theory suggests that Venus originally rotated in the same direction as Earth, but was flipped over by a massive impact early in its history. Another possibility is that tidal interactions with the Sun gradually slowed Venus's rotation and eventually reversed it. Whatever the cause, this slow rotation means that any given location on Venus experiences around 2 months of continuous daylight, followed by 2 months of continuous night. Though the thick clouds mean that the surface never receives direct sunlight, and remains in a perpetual dim orange glow. What would happen to a human who somehow found themselves on Venus's surface without protection? Death would be instantaneous and come from multiple directions. The crushing atmospheric pressure would immediately compress the body, while the extreme heat would simultaneously cause bodily fluids to boil despite the pressure. The carbon dioxide atmosphere would be unbreathable, and the trace amounts of sulfuric acid in the lower atmosphere would begin to chemically attack any exposed surfaces. There is perhaps no environment in the solar system where an unprotected human would die more quickly. Even with our most advanced technology, exploring Venus's surface remains extraordinarily challenging. The Soviet Venera landers, the most successful Venus surface missions to date, were technological marvels of their time. They featured pressure vessels akin to deep-sea submersibles, cooling systems that use circulating refrigerants, and sapphire windows to protect their camera lenses. Despite these precautions, none survived longer than 2 hours on the surface before succumbing to the hellish conditions. Modern proposals for Venus surface exploration include mechanical rovers with minimal electronics, clockwork computers resistant to heat, and high-temperature electronics based on silicon carbide rather than conventional silicon. Some visionary concepts even suggest balloon-borne habitats that would float in the more temperate regions of Venus's upper atmosphere, where temperatures and pressures are surprisingly Earth-like at an altitude of about 50 to 60 kilometers above the surface. Despite its hostile surface, Venus's upper atmosphere presents one of the most Earth-like environments in the solar system outside of Earth itself. At an altitude of about 50 kilometers, the temperature ranges from 0 to 50 degrees Celsius, and the pressure is similar to Earth's sea level. This has led some astrobiologists to speculate about the possibility of microbial life existing in these cloud layers. The highly acidic environment would be challenging, but not impossible for life. On Earth, extremophile organisms have been found thriving in similarly acidic conditions, such as the Rio Tinto in Spain, where the pH approaches 0. In 2020, scientists announced the detection of phosphine in Venus's upper atmosphere, a gas that on Earth is primarily produced by microbial life in oxygen-poor environments. While subsequent analyses have questioned this detection, the controversy has reinvigorated interest in Venus as a potential abode for alien life, albeit in its clouds rather than on its scorching surface. If confirmed, the presence of life in Venus's clouds would have profound implications for astrobiology, suggesting that life could adapt to environments far more extreme than previously thought. Venus presents a unique case study in comparative planetology by understanding how Venus and Earth, two planets so similar in size, composition, and distance from the Sun, evolved so differently. Scientists gain insights into the factors that determine planetary habitability. Venus teaches us that a planet's fate isn't determined solely by its position in the solar system, but by complex interactions between its atmosphere, surface, interior, and the star it orbits. The stark differences between Venus and Earth likely resulted from what scientists call divergent evolution, small initial differences that became amplified over time through feedback mechanisms. Venus's slightly closer position to the Sun may have been just enough to trigger the runaway greenhouse effect that transformed it into the hellscape we observe today. This understanding informs our search for habitable exoplanets, suggesting that the traditional concept of a habitable zone around stars may be too simplistic. Small differences in atmospheric composition, rotation rate, or geological activity could make the difference between an Earth-like paradise and a Venus-like inferno. Our understanding of Venus has evolved dramatically since the early space age. The planet's perpetual cloud cover made it a canvas for human imagination, with some early speculations suggesting it might harbor swamps or tropical forests. The first spacecraft to visit Venus, NASA's Mariner 2 in 1962, began to reveal its true nature by measuring its extreme surface temperature. Subsequent missions, including multiple Soviet Venera probes, NASA's Pioneer Venus mission, and the European Space Agency's Venus Express, have gradually unveiled the planet's hellish characteristics. Scientific interest in Venus has experienced a renaissance in recent years. NASA has approved 2 new Venus missions, Da Vinci Plus and Veritas. scheduled to launch in the late 2020s. The European Space Agency has also approved the Envision mission to Venus. These spacecraft will use advanced instruments to peer through Venus's clouds, map its surface in unprecedented detail, and even descend through its atmosphere to directly sample its composition. This renewed focus on Venus reflects a growing recognition of the planet's importance for understanding climate evolution, planetary habitability, and the factors that determine whether a world becomes an Earth-like haven or a Venus-like hell. Venus's position as a cautionary example of climate disaster has taken on new significance in the era of human-induced climate change on Earth. While Earth isn't at risk of a full Venus-like transformation, the basic physics of the greenhouse effect operates identically on both planets. Venus stands as an extreme demonstration of how a planet's climate can permanently change when certain thresholds are crossed. By studying Venus, scientists gain insights into climate feedback mechanisms, atmospheric chemistry, and planetary-scale environmental tipping points that inform our understanding of Earth's changing climate. The legacy of Venus in human culture extends beyond scientific interest. As the brightest, natural object in our night sky after the Moon, Venus has figured prominently in mythology, art, and literature across cultures. To the ancient Greeks and Romans, it was associated with the goddess of love and beauty. Many indigenous cultures developed their own myths and interpretations of this brilliant, wandering light. In modern science fiction, Venus has appeared as everything from a jungle world to a cautionary tale of environmental catastrophe. The stark reality of Venus, revealed through scientific exploration, provides a fascinating contrast to these cultural interpretations. The planet named for the goddess of beauty harbors some of the most hostile conditions in the solar system. As we leave this hellish world so tantalizingly close to our own, we're reminded that cosmic horrors need not be distant. Venus orbits just next door, in astronomical terms, a constant presence in our evening and morning skies, silently warning us of what can happen when a planet's climate systems are pushed beyond their limits. Its beauty when seen from Earth belies the infernal conditions that await beneath its sulfuric acid clouds, a deceptive facade much like the next world on our tour, which appears to be made of beautiful blue ice, but harbors a paradoxical state of matter that seems to defy common sense. But what about a world that's literally made of burning ice? Gliese 436b introduces us to one of the most mind-bending paradoxes in our tour of cosmic nightmares, a world covered in ice that burns at hundreds of degrees. Located approximately 33 light-years from Earth in the constellation Leo, this exoplanet represents perhaps the most profound contradiction we've encountered so far. A place where the familiar states of matter as we understand them on Earth break down completely, replaced by exotic conditions that seem to defy common sense. Discovered in 2004 by the California and Carnegie Planet Search Team, led by R. Paul Butler and Jeffrey Marcy, Gliese 436b orbits a red dwarf star, roughly half the mass of our Sun. The planet itself is categorized as a warm Neptune, a gas giant similar in size and mass to Neptune in our solar system, but orbiting much closer to its star. With a mass of about 22 Earth masses and a radius roughly 4 times Earth's, Gliese 436b occupies a middle ground between the massive gas giants like Jupiter and smaller rocky worlds like our home planet. What makes this world truly extraordinary is its composition and the bizarre physical state it creates. Based on density measurements and spectroscopic observations, scientists have determined that a significant portion of Gliese 436b consists
Imagine
of
a
water,
time before anything
but
existed.
not water as we know
No
it on
stars,
Earth.
no
On this
planets,
strange world,
no light,
water exists
no
in a state
darkness,
called Ice
not
X
even space itself.
or Ice 10.
The universe
solid
we know
form
and
of
live in
water
today
that
was
remains
once a blank
frozen
canvas,
despite
so
surface
empty and
temperatures
silent.
estimated
It was
at around
almost as if it wasn't there at
439
all.
degrees Celsius.
But then, in a
hot
moment,
enough
we
to
can
melt
hardly
lead,
fathom.
zinc,
Everything changed.
and many other metals.
This is the story
This apparent
of how our
contradiction,
universe came to life.
ice that exists at temperatures
But here's the
far
catch.
above water's normal
It didn't
boiling
come
point,
from somewhere.
stems
It came
from the
from
extreme
nothing.
pressure conditions
And
on
nothingness
Gliese
so complete,
436b,
so profound,
the planet's
that it defies
gravitational
everything
pull,
we think we know about the
combined with
laws
the
of
weight
reality.
of its thick atmosphere,
How did it
create
happen?
surface pressures
What
millions
sparked
of
the birth
times
of
greater
everything
than
around
Earth's
us?
atmospheric pressure at sea level.
This journey begins
Under these
in the most
crushing
unimaginable
conditions,
place.
water molecules are forced into
place where
rigid,
everything,
crystalline structures
even the idea
that
of
remain
beginning,
solid even at
didn't even
temperatures that
exist.
would normally vaporize water instantly. The pressure on Gliese 436b is almost unimaginable by terrestrial standards.
No
At its
stars,
surface,
no
the pressure
planets,
likely
no
exceeds
light,
8
no
gigapascals,
darkness, not
over
even space
80,000
itself.
times Earth's
The
atmospheric
universe
pressure
we
at sea
know and
level.
live in today
This is
was once a
comparable to
blank
the pressure
canvas,
found hundreds of
so
kilometers
empty
deep in
and
Earth's
silent.
mantle.
It was
As
almost
you
as if it
descended
wasn't
through the
there at
planet's
all.
atmosphere toward
But
its
then,
solid
in a moment
layers,
we can
the
hardly
pressure would
fathom,
increase
everything
exponentially,
changed.
eventually
This
reaching
is the
levels where the
story
very
of
electrons
how
and
our
atoms are
universe
compressed,
came to life.
fundamentally
But here's the
altering how
catch.
matter behaves.
It didn't come from somewhere.
Hot ice
It
represents
came from
one of the
nothing.
most exotic
A
states of
nothingness
matter
so
we've
complete,
discovered in the universe.
so profound,
Water,
that it
a
defies
simple molecule
everything
essential
we
to
think
life
we know
on
about
Earth,
the laws
exhibits
of
extraordinarily
reality.
complex
How did
behavior
it happen?
under extreme
What
conditions.
sparked the birth
On
of
Earth,
everything
we're
around
familiar
us?
with water in
This
its three
journey
common
begins
phases:
in the most unimaginable
solid ice,
place,
liquid water,
a place where
and gaseous
everything,
steam or
even
water
the idea
vapor.
of beginning,
But scientists have identified at
even
least 18
exist.
different crystalline phases of ice that form under various temperature and pressure conditions, with Ice X being among the most exotic. The progression of ice phases reveals the remarkable versatility of water as a chemical compound. Ordinary ice on Earth, known as Ice H, Ice 1H, has a hexagonal crystal structure that creates the six-sided symmetry we see in snowflakes. As pressure increases, water molecules rearrange into more compact structures, Ice 2, 3, V, and 6, each with unique crystal lattices. At the pressures found on Gliese 4, 36b, Ice 7, and Ice X become stable, with Ice X representing a fundamental rearrangement where hydrogen atoms position themselves precisely between oxygen atoms, creating a symmetric cubic structure unlike any naturally occurring ice on Earth. What would this burning ice look like up close? Unlike the transparent or whitish ice we're familiar with on Earth, Ice X would appear dark and dense, with a structure more akin to metal than conventional ice. Its oxygen and hydrogen atoms arrange themselves in a symmetric cubic pattern fundamentally different from the hexagonal structure of common ice. This exotic water wouldn't melt if heated. Instead, if the pressure were maintained and the temperature increased further, it would eventually transition directly to a superurionic state, where hydrogen atoms flow freely through a fixed lattice of oxygen, creating a substance that behaves simultaneously as a solid and a liquid. This superionic phase represents yet another exotic state that might exist deeper within Gliese 436b. In this state, oxygen atoms remain locked in a crystal structure, while hydrogen atoms break free, moving through the oxygen lattice as charged particles, protons. This creates a material that conducts electricity like a metal while maintaining the rigid structure of a solid, essentially a solid that flows with electric current. Laboratory experiments on Earth have only recently confirmed the existence of superionic ice, requiring both extreme pressure and high temperature to create this exotic phase. The discovery of Gliese 436b's water-rich composition came through a combination of mass and radius measurements that revealed the planet's own Gliese 436b used the radial velocity method, measuring the tiny wobble the planet induces in its parent star as they orbit a common center of mass. Follow-up observations revealed that the planet also transits its star from our perspective, allowing astronomers to measure its radius as it passes in front of its stellar host. This fortunate alignment, occurring in only a small percentage of planetary systems due to orbital geometry, provided crucial data for determining the planet's density and inferring its composition. The combination of mass and radius measurements gave scientists the planet's average density, approximately 2 grams per cubic centimeter, significantly less dense than Earth, 5.5 grams per cubic centimeter, but denser than Saturn, 0.7 grams per cubic centimeter. This intermediate density suggested a composition different from both rocky terrestrial planets and hydrogen-dominated gas giants. Models indicated a substantial water layer was necessary to explain the observed density, leading to the conclusion that Gliese 436b contains a significant fraction of water existing in exotic high-pressure phases. This hot ice world challenges our understanding of planetary formation and evolution. Traditional models suggest that planets like Neptune form far from their stars, where temperatures are low enough for water and other volatiles to condense into ices. Gliese 436b likely formed in a similar way, but subsequently migrated inward to its current close orbit. During this migration, the planet's outer layers would have been subjected to intense heating from its star, potentially vaporizing significant portions of its original ice content. The fact that it retained so much water suggests either that the migration occurred relatively recently in astronomical terms, or that the planet's gravitational field was strong enough to hold onto its water despite the increased temperature. The orbit of Gliese 436b adds another layer of complexity to this strange world. The planet circles its star in just 2.6 Earth days, maintaining an oval-shaped orbit rather than the more circular path we might expect for a planet so close to its star. This eccentric orbit suggests gravitational interactions with other, as yet undetected planets in the system, or perhaps a relatively recent migration that hasn't had time to circularize. As the planet follows this elliptical path, it experiences varying levels of stellar heating, potentially creating temperature fluctuations that drive complex atmospheric dynamics. The eccentric orbit of Gliese 436b creates another unusual effect: significant tidal heating. As the planet moves closer to and further from its star during each orbit, gravitational forces stretch and compress its interior, generating frictional heat. This tidal heating supplements the energy received from the star, potentially increasing the planet's internal temperature and contributing to its exotic state. The process is similar to what occurs on Jupiter's moon Io, where tidal interactions with Jupiter create intense volcanic activity, but on Gliese 436b, the effect operates on a much larger scale with more extreme consequences. What would happen to a human unfortunate enough to visit this world of burning ice? As with the other planets we've explored, death would be instantaneous and come from multiple directions. The crushing pressure would flatten any unprotected visitor instantly. The extreme heat would incinerate organic material even as the exotic pressure conditions created solid ice all around. The atmosphere, primarily consisting of hydrogen and helium, with traces of water vapor and other compounds, would be unbreathable. Even with theoretical advanced technology, the combination of heat and pressure makes Gliese 436b essentially inaccessible to direct exploration. If we imagine a theoretical observer somehow protected from these extreme conditions, the experience of Gliese 436b would be utterly alien. The surface, if there is a discrete boundary that could be called a surface, would likely be a dark, dense layer of exotic ice, possibly with a consistency more like warm asphalt than anything we recognize as ice. Above this would be a thick atmosphere glowing with heat, potentially with unusual cloud formations composed of metallic or silicate compounds, rather than the water-based clouds familiar on Earth. The boundary between solid and gaseous phases might be blurred, with a gradual transition rather than a sharp interface. The parent star, Gliese 436, is significantly smaller and cooler than our Sun. This red dwarf emits most of its energy in the infrared, rather than visible wavelengths, giving its light a reddish hue. Standing on Gliese 436b, if such a thing were somehow possible, the star would appear as a large, deep red-orange disk in the sky, casting an eerie russet illumination across the exotic landscape. The close proximity to this star means it would appear much larger in the sky than our Sun appears from Earth, dominating the visual field with its ruddy glow. Red dwarf stars like Gliese 436 present unique conditions for their planets. These stars are the most common type in our galaxy, accounting for approximately 70% of all stars. They burn their nuclear fuel much more slowly and efficiently than larger stars, with lifespans measured in trillions rather than billions of years. This longevity means that planets orbiting red dwarfs have stable energy sources for time periods vastly exceeding the current age of the universe. However, these stars also emit powerful flares, especially when young, that can strip away planetary atmospheres and bombard surfaces with radiation. The Gliese 436 star is approximately 4 billion years old, roughly the same age as our Sun, but will continue to shine steadily for trillions of years to come. This stability raises an interesting question about the long-term fate of Gliese 436b, while the planet currently maintains its exotic state of hot ice. How will it evolve over the immense timescales of its star's lifetime? Will it gradually lose its atmosphere to space? Will its orbit change due to gravitational interactions with other bodies in the system? The answers to these questions remain speculative, but the system offers a glimpse into potential planetary evolution over timescales far exceeding Earth's entire existence. The internal structure of Gliese 436b likely consists of layers with distinct compositions. At its center probably lies a core of rock and metal, similar to but larger than Earth's core. Surrounding this would be a thick mantle composed primarily of exotic, high-pressure forms of water ice, including Ice X and possibly other phases. Above this would be a relatively thin atmosphere of hydrogen, helium, and water vapor. This structure differs significantly from both gas giants like Jupiter, which have no solid surface, and terrestrial planets like Earth, which have relatively thin mantles compared to their core size. Gliese 436b represents an intermediate category, sometimes called ice giants or water worlds. The internal temperature gradient of Gliese 436b creates conditions for multiple phase transitions within its mantle. Deeper regions might contain supersonic water, where hydrogen atoms flow freely through an oxygen lattice. Intermediate layers could consist of Ice X and other exotic solid phases. Near the surface, where pressure decreases but temperature remains high, there might be a transition to supercritical water, a state that blurs the distinction between liquid and gas, having properties of both simultaneously. This layered structure creates a planet that defies simple categorization, with properties unlike any world in our solar system. The magnetic field of Gliese 436b remains a subject of theoretical modeling rather than direct observation. If supersonic water exists in its interior, this electrically conductive material could generate a magnetic field as it moves due to the planet's rotation and internal heat flow. Such a magnetic field would interact with the charged particles emitted by its star, potentially creating aurora-like phenomena in its upper atmosphere. Future observations with more sensitive instruments might detect evidence of this magnetic field through its interaction with the stellar wind. Could life exist on such a bizarre planet? By any definition of life as we understand it, Gliese 436b would be sterile. The extreme temperatures and pressures would destroy organic molecules, and the solid state of water would prevent the chemical reactions necessary for Earth-like biochemistry. However, the existence of such exotic worlds expands our understanding of the environments where matter can organize itself in complex ways. The boundary between living and non-living systems becomes increasingly blurred under conditions so alien to our experience. Some astrobiologists have speculated about the possibility of life in the uppermost layers of atmospheres of planets like Gliese 436b, where temperatures and pressures might be more moderate. Floating microorganisms might theoretically adapt to these conditions, perhaps using the temperature gradients between different atmospheric layers as an energy source. While highly speculative, such hypotheses remind us that life might find ways to adapt to environments we consider impossible based on our Earth-centric perspective. The discovery of Gliese 436b and similar exoplanets has forced scientists to expand their classification systems for planetary types. The traditional division between terrestrial, rocky, planets, and gas giants no longer adequately captures the diversity of worlds we're finding. Intermediate categories like mini-Neptunes, super-Earths, and water worlds have emerged to describe planets with no direct analogues in our solar system. Gliese 436b, with its significant water content existing in exotic high-pressure phases, represents a class of planets that may be common throughout the galaxy, but absent from our home system. These new planetary categories have implications for our understanding of planetary system formation and evolution. The absence of mini-Neptunes and hot Neptunes like Gliese 436b in our solar system raises questions about the factors that determine a system's final architecture. Was there something unique about our solar system's formation that prevented such worlds from developing or surviving? Or did similar planets form initially but then migrate or be ejected through gravitational interactions? The answers to these questions inform our broader understanding of how common systems like our own might be in the galaxy. The existence of hot ice on Gliese 436b connects to research being conducted in laboratories on Earth, where scientists use specialized equipment like diamond anvil cells to create extreme pressures that replicate the conditions inside giant planets. These experiments have confirmed the existence of exotic ice phases and other strange states of matter, validating the theoretical models used to understand worlds like Gliese 436b. The study of such extreme planetary environments drives advancements in material science, high-pressure physics, and our fundamental understanding of how matter behaves under conditions far beyond those naturally occurring on Earth. Laboratory work on high-pressure ice phases has direct applications beyond astronomy. Understanding how water behaves under extreme conditions informs research in materials science, potentially leading to the development of new substances with useful properties. It also has applications in geophysics, helping scientists understand processes deep within Earth and other planets. The strange physics of supersonic ice, where a substance behaves simultaneously as a solid and a conductor, might eventually inform the development of new types of electronic or energy storage materials. Recent observations of Gliese 436b have revealed additional complexities in its atmosphere and composition. Ultraviolet light measurements from the Hubble Space Telescope detected an extended hydrogen atmosphere being actively lost to space, creating a comet-like tail as the planet orbits its star. This atmospheric escape provides evidence that the planet is still evolving, gradually losing its lighter elements to space while retaining its heavier components, including the exotic water ice that makes up much of its mass. The atmospheric loss observed on Gliese 436b occurs through a process called hydrodynamic escape. The planet's upper atmosphere is heated by ultraviolet radiation from its star, causing hydrogen atoms to move fast enough to escape the planet's gravitational pull. As these atoms stream away, they create a tenuous tail extending into space, somewhat like a comet's tail, but composed primarily of hydrogen rather than dust and ice. Over billions of years, this process could significantly alter the planet's composition, potentially leaving it with a higher proportion of heavier elements as the lighter hydrogen is lost to space. The future of research on worlds like Gliese 436b lies with next-generation telescopes capable of more detailed atmospheric characterization. The James Webb Space Telescope, with its unprecedented infrared capabilities, is particularly well-suited for studying planets around red dwarf stars, which emit primarily in the infrared. Future observations may reveal more details about the composition of Gliese 436b's atmosphere, the temperature structure at different altitudes, and potentially even the composition of its exotic mantle. Upcoming ground-based extremely large telescopes, such as the European Extremely Large Telescope and the Giant Magellan Telescope, will provide additional capabilities for studying exotic worlds like Gliese 436b. These instruments will combine enormous light-gathering power with advanced adaptive optics systems to overcome the blurring effects of Earth's atmosphere. Their high-resolution spectroscopic capabilities will allow for more detailed chemical analysis of exoplanet atmospheres, potentially revealing minor components that current instruments cannot detect. The study of Gliese 436b also connects to broader questions about the distribution of water throughout the galaxy. Water appears to be a common molecule in planetary systems, existing in various states depending on local conditions. From the liquid oceans of Earth to the icy moons of the outer solar system, from the water vapor in stellar nurseries to the exotic high-pressure ices of planets like Gliese 436b, water demonstrates a remarkable range of behaviors under different conditions. Understanding these various manifestations helps scientists track the movement of this essential molecule through the processes of planetary formation and evolution. Water's ubiquity in the cosmos stems from the abundance of its constituent elements: hydrogen, the most common element in the universe, and oxygen, forged in the hearts of stars and spread through space by stellar explosions. These elements readily combine to form water under a wide range of conditions. Astronomical observations have detected water in interstellar clouds, protoplanetary disks around young stars, and the atmospheres of planets and moons throughout our solar system and beyond. This prevalence suggests that water, in its various forms, plays a fundamental role in the formation and evolution of planetary systems throughout the galaxy. Gliese 436b represents just one example of the exotic water worlds that may be common in our galaxy. Other discovered exoplanets such as GJ1214b and TOI270b show evidence of similar compositions with significant amounts of high-pressure ices. These planets form a distinct class that challenges traditional models of planetary formation and composition. Their prevalence suggests that water, in its various exotic forms, may be one of the most common planetary building materials in the universe, taking forms far different from the familiar liquid that covers much of Earth's surface. The discovery and characterization of planets like Gliese 436b represent remarkable achievements in modern astronomy. Just 3 decades ago, the very existence of planets beyond our solar system remained unconfirmed. Today, astronomers not only detect these distant worlds, but analyze their compositions, atmospheric structures, and even weather patterns. This rapid progress speaks to the power of modern observational techniques and the ingenuity of scientists developing new methods to probe the cosmos. As we leave this world of paradoxical burning ice, we're reminded that the universe doesn't conform to our intuitions based on everyday experience. Physics at extreme scales creates conditions where familiar substances behave in ways that seem contradictory or impossible. The hot ice of Gliese 436b exemplifies how the same chemical compound, H2O, essential to life on Earth, can manifest in radically different forms under altered conditions. This adaptability of matter under varying circumstances underlies the incredible diversity of worlds we're discovering throughout the galaxy. Our next destination takes us away from the solid surfaces and exotic ices we've encountered so far, to a world of a completely different nature, a planet covered in endless, unfathomably deep oceans. Here, the horror lies not in extreme temperatures or exotic states of matter, but in the vast, dark unknown lurking in abyssal depths that make Earth's deepest ocean trenches seem like shallow puddles by comparison. Some planets are terrifying not because of their surface, but because of what lurks beneath. TRAPPIST-1d, the ocean planet with hidden horrors. Imagine a world where there is no land at all, no continents, no islands, not even a single rocky outcrop breaking the surface of an endless planet-spanning ocean. This is the terrifying reality of TRAPPIST-1d, the 4th planet in the TRAPPIST system, located about 40 light-years from Earth in the constellation Aquarius. Unlike Earth, where oceans cover roughly 71% of our surface, TRAPPIST-1d is believed to be completely enveloped in water. But this isn't just any ocean. Astronomers estimate that this global sea could be hundreds of kilometers deep, creating crushing pressures that would make our deepest ocean trenches seem like shallow puddles in comparison. The TRAPPIST system itself is unusual, orbiting an ultra-cool dwarf star that's only about 8% the mass of our Sun. This tiny, dim star bathes its 7 planets in a reddish glow, creating an alien twilight that would make our familiar blue skies seem like a distant dream. TRAPPIST-1d orbits within what astronomers call the habitable zone, the region where liquid water can exist on a planet's surface. But that doesn't mean it's hospitable by any stretch of the imagination. The gravitational forces between TRAPPIST-1d and its host star have likely locked the planet into a synchronous rotation, meaning one side perpetually faces the star, while the other remains in eternal darkness. This creates a planet of stark contrasts, one hemisphere constantly bathed in dim red light, the other shrouded in permanent night, with only a thin band of permanent twilight separating these two extremes. What makes this world truly nightmarish isn't just its endless ocean, but what could be lurking beneath those alien waves. On Earth, our deepest ocean trenches, like the Mariana Trench, plunge to depths of about 11 kilometers, creating environments of crushing pressure, near freezing temperatures, and total darkness. Yet even in these extreme conditions, life finds a way to exist. Bizarre creatures with translucent bodies, bioluminescent features, and feeding strategies that seem alien even by Earth standards. Now, imagine an ocean not just 11 kilometers deep, but potentially hundreds of kilometers in depth. The pressure at the bottom would be millions of times greater than Earth's atmospheric pressure at sea level. Under such extreme conditions, water itself begins to behave differently, forming exotic ice crystals that, despite the tremendous heat and pressure, remain solid due to the bizarre physics at play. These deep ocean layers could be home to forms of life so radically different from anything on Earth that we might not even recognize them as living beings. Without sunlight, such creatures would need to evolve alternative energy sources, perhaps harnessing the chemical energy from hydrothermal vents or developing entirely novel metabolic pathways unknown to Earth biology. In the eternal darkness of TRAPPIST-1d's deepest waters, evolution could have taken truly nightmarish turns. Imagine predatory organisms larger than blue whales, with sensory systems that can detect the slightest movement from kilometers away. Creatures that have never known light, developing hunting strategies based entirely on pressure waves, electromagnetic fields, or even senses we humans can't comprehend. The most terrifying aspect of TRAPPIST-1d might be that we simply cannot know what's down there. Our most advanced telescopes can barely detect the planet itself, let alone peer beneath its watery surface. If we ever sent a probe, it would have to contend not just with the 40 light-year journey, but with the crushing pressures that would destroy any spacecraft designed with current human technology. What makes ocean worlds like TRAPPIST-1d particularly intriguing to scientists is their formation process. Unlike Earth, which likely formed with a mix of rocky material and some water, ocean planets are thought to have migrated from the outer regions of their star systems, where they accumulated massive amounts of ice before moving inward, where that ice melted into liquid oceans. This migration suggests that ocean worlds might be more common than previously thought. What's more, their global oceans provide a natural laboratory for studying how life might evolve in isolation from the geological processes that have shaped Earth's evolutionary history. But the nightmare doesn't end with the crushing depths. The synchronous rotation of TRAPPIST-1d creates another terrifying scenario, the possibility of megastorms that never end. On the boundary between the day and night sides, where warm air meets cold, permanent hurricane-like storms could rage with winds exceeding 500 kilometers per hour, creating waves that would dwarf our most fearsome tsunamis. Imagine waves as tall as skyscrapers, constantly crashing across a twilight zone of perpetual storm. The energy contained in such a weather system would be enough to power all of human civilization for centuries. Yet here, it's just another feature of this alien hellscape. If humans ever attempted to visit or colonize such a world, they would face challenges beyond our current technological capabilities. Any settlement would need to be either floating on the turbulent surface, constantly at the mercy of planet-spanning storms, or submerged to escape the surface chaos, only to face the crushing pressures and unknown creatures lurking in the depths. The atmospheric composition above TRAPPIST-1d's oceans presents another mystery. If the planet truly is covered in a global ocean, its atmosphere would likely be saturated with water vapor, creating a powerful greenhouse effect that could raise surface temperatures well beyond what we'd consider habitable. On the other hand, if the planet formed with large amounts of water, it might have enough of it to create bizarre high-pressure ice layers at depth, despite surface temperatures that could boil Earth's oceans. What's particularly haunting about TRAPPIST-1d is that it sits in what astronomers call the habitable zone of its star, meaning it receives just the right amount of energy to potentially maintain liquid water on its surface. This has led some optimistic scientists to speculate that it could harbor life, but this optimism ignores the nightmarish reality of what that life would have to endure: crushing pressures, possible extreme temperatures, and a world permanently divided between endless twilight and eternal darkness. If life does exist in the depths of TRAPPIST-1d, it would be so radically different from Earth life that communication or even recognition might be impossible. Imagine highly intelligent beings that have evolved in an environment where solid ground doesn't exist, where up has little meaning, and where darkness is the natural state of existence. Their perception of reality, their technology, their very concept of existence would be utterly alien to human understanding. The ocean depths of Earth remain largely unexplored, with less than 20% of our own oceans mapped in high resolution. We've discovered creatures on Earth that can survive without oxygen, thrive in radioactive environments, or withstand pressures that would crush a submarine. Now imagine what evolution might produce given billions of years on a world where the entire planetary surface is an ocean potentially hundreds of kilometers deep. Some scientists speculate that ocean worlds like TRAPPIST-1d might actually be the most common type of habitable planet in the galaxy. If that's true, then the dominant form of life in the universe might be aquatic rather than terrestrial. Our science fiction visions of alien civilizations building cities and gazing at the stars could be completely backward. The most advanced civilizations might exist in lightless ocean depths, with no concept of the broader universe beyond their watery world. The most unsettling aspect of TRAPPIST-1d is perhaps how it challenges our very definition of habitability. We tend to think of habitable worlds as Earth-like: moderate temperatures, mix of land and water, oxygen-rich atmosphere. But the universe might have a much broader definition. Life adapted to the crushing depths of an ocean world might find Earth's conditions just as lethal as we would find theirs. From a human perspective, ocean worlds like TRAPPIST-1d represent one of the most paradoxical types of planets, potentially habitable in the technical sense that they could support liquid water, yet utterly inhospitable to human life, without technologies far beyond our current capabilities. They are simultaneously fascinating and terrifying, promising the possibility of alien life while virtually guaranteeing that such life would be more alien than our wildest imagination. If we were somehow able to descend into the depths of TRAPPIST-1d's global ocean, what might we find? Perhaps the water becomes increasingly dense and strange as pressure increases, eventually transitioning into exotic states of matter unknown on Earth. Perhaps the ocean floor, if there even is one, hosts undersea volcanoes that dwarf anything on Earth, creating vast hydrothermal vent systems that support sprawling ecosystems in the darkness. Or maybe, in the most terrifying possibility, the ocean has no bottom at all, just layers of increasingly exotic water states, becoming denser and stranger with depth, creating a world where down continues forever into an abyss of increasing pressure and alienness. The technology required to explore such a world would be far beyond our current capabilities. Any probe would need to withstand pressures millions of times greater than Earth's atmosphere, temperatures that could range from near freezing to hundreds of degrees Celsius depending on depth, and an environment where even the chemistry of water itself behaves in ways our science struggles to model accurately. And yet, despite all these horrors, TRAPPIST-1d and planets like it represent some of our best chances for finding extraterrestrial life. The stable environment of a global ocean, protected from the harmful radiation of space by kilometers of water, could provide the perfect cradle for life to emerge and thrive, following evolutionary paths wildly different from those on Earth. Our own ocean depths have consistently surprised us with their biodiversity and the extreme adaptations of deep-sea creatures. From giant squid with eyes the size of dinner plates to fish with transparent heads From bacteria that can survive in near-boiling water to worms that thrive in the toxic environments around hydrothermal vents. Earth's deep oceans give us just a glimpse of what might be possible on a world where the entire planet is an ocean, potentially hundreds of times deeper than ours. If intelligent life has evolved in such an environment, it might have developed technologies completely different from our own. Without access to fire or metals in their natural environment, such beings might harness biological processes instead, creating living technologies that grow rather than being built. They might communicate through pressure waves or bioluminescence rather than sound or radio waves. Their mathematics, their art, their very conception of physics might be utterly alien to human understanding. The TRAPPIST system was first detected in 2016 using the Transiting Planets and Planetesimals, small telescope in Chile, and later confirmed by observations from NASA's Spitzer Space Telescope. The discovery of 7 Earth-sized planets orbiting this tiny red dwarf star generated tremendous excitement in the astronomical community, particularly because several of these worlds, including TRAPPIST-1d, orbit in the star's habitable zone. But being in the habitable zone doesn't guarantee habitability. Recent models suggest that planets orbiting red dwarf stars face unique challenges, including strong stellar flares that could strip away their atmospheres and intense tidal forces that lock one side of the planet permanently facing the star. These factors could transform what might otherwise be paradise worlds into nightmarish hellscapes. For TRAPPIST-1d, the combination of tidal locking and a global ocean creates a scenario where massive amounts of water could be continuously evaporated from the day side and frozen on the night side, potentially creating a world split between boiling seas and ice sheets kilometers thick. Over geological time, this process might even transfer enough water to the night side to expose land on the day side, creating a planet split not between day and night, but between scorching desert and frozen wasteland, with only a narrow band of habitability between. The more we learn about exoplanets like TRAPPIST-1d, the more we appreciate the delicate balance of conditions that make Earth so perfectly suited for human life. Our planet's mix of land and water, its protective magnetic field, its stable orbit around a well-behaved star. These factors aren't necessarily the norm in the universe. Ocean worlds challenge our perception of what makes a planet habitable. They suggest that life, if it exists elsewhere in the cosmos, might thrive in environments we find utterly hostile. The creatures that call such worlds home would likely find Earth just as inhospitable as we would find their watery realm. As our telescopes improve and our understanding of planetary formation deepens, we're likely to discover many more ocean worlds throughout the galaxy. Each will present its own horrors and wonders, its own unique set of conditions that might support forms of life beyond our imagination. TRAPPIST-1d serves as a haunting reminder that the universe doesn't conform to human notions of habitability or comfort. It exists as it is, a world of endless ocean, crushing pressure, and eternal twilight, indifferent to whether humans find it hospitable or horrifying. And that, perhaps, is the most terrifying truth about the cosmos. It wasn't made for us, and most of it exists in states that are fundamentally hostile to human life. In the end, ocean worlds like TRAPPIST-1d are both a promise and a warning. They promise that the universe is filled with environments where life might take hold in forms we can barely imagine. But they warn us that if we ever venture beyond our comfortable terrestrial cradle, we'll find a cosmos largely indifferent or actively hostile to our fragile human form. As we gaze at the dim red star of TRAPPIST in our telescopes, we're looking at a system that might harbor life unlike anything we've ever known. Creatures adapted to pressures that would crush our strongest submarines. Beings that have never seen the stars or felt solid ground beneath them. Intelligences that might perceive reality in ways fundamentally different from human consciousness. And that is the true horror of TRAPPIST-1d, not just its physical extremes, but the possibility that it represents a kind of habitable world far more common than Earth-like planets, suggesting that if we ever do encounter alien life, it might be so fundamentally different from us that meaningful communication or understanding could be impossible. The ocean planet TRAPPIST-1d reminds us that in the vast cosmic ocean, Earth is but a tiny island of familiarity in an endless sea of strangeness, and beneath the waves of distant worlds, horrors and wonders beyond human imagination may lurk, waiting to be discovered. PSR B1257+12c, the planet in a pulsar's wrath. In the vast expanse of space, there exist worlds so hostile, so incredibly dangerous, that they challenge our very understanding of what constitutes a planet. Among these nightmarish realms, perhaps none is more terrifying than PSR B1257+12c, a world that orbits not a living star, but a stellar corpse, a rapidly spinning pulsar that bathes its planetary system in deadly radiation every single second of every single day. Located approximately 2,300 light-years from Earth in the constellation Virgo, this world has the dubious honor of being among the first exoplanets ever discovered back in 1992. But unlike the thousands of worlds discovered since then, this planet exists in what can only be described as one of the most hostile environments imaginable, the gravitational grip of a pulsar. To understand the horror of this world, we must first understand what a pulsar actually is. When a massive star reaches the end of its life, it can explode in a supernova, one of the most violent events in the universe. What remains afterward is sometimes a pulsar, essentially a city-sized ball of neutrons spinning at incredible speeds, sometimes rotating hundreds of times per second. These stellar remnants are among the densest objects in the universe, with a single teaspoon of pulsar material weighing roughly 1 billion tons. But what makes pulsars truly terrifying is that they serve as cosmic lighthouses, shooting beams of intense radiation from their magnetic poles as they spin. These beams contain high-energy particles and radiation across the electromagnetic spectrum, from radio waves to deadly gamma rays. When these beams sweep across our line of sight, we detect regular pulses of radiation, hence the name pulsar. PSR B1257+12 orbits such a cosmic monster, a pulsar that rotates approximately 161 times every single minute. This means that every third of a second, this planet is bathed in a fresh wave of devastating radiation. The pulsar itself is only about 20 kilometers in diameter, roughly the size of a city. Yet it contains more mass than our Sun, creating a gravitational field so intense that it warps the very fabric of space-time around it. What makes this particular planet even more mind-boggling is that it shouldn't exist at all. The prevailing theory for planet formation involves worlds coalescing from the disk of gas and dust surrounding a young star. But the supernova that created this pulsar should have obliterated any planets in the system. The explosion would have released more energy in a few seconds than our Sun will produce in its entire 10 billion year lifetime, creating a shockwave capable of destroying everything in its path for light years in every direction. So how does PSR B1257+12c exist at all? Astronomers believe it may be a second-generation planet, formed from the debris left over after the supernova explosion. Alternatively, it could be the remnant core of a once massive companion star that was partially consumed and shredded by the progenitor star before it went supernova. Either way, this planet represents a type of world that has experienced cosmic violence beyond human comprehension. The planet itself is approximately 4 times the mass of Earth, making it what astronomers would classify as a super-Earth. It orbits its pulsar at a distance of approximately 0.36 astronomical units, roughly a third of the distance between Earth and our Sun. At this distance, if the pulsar were a normal star, the planet might be in the habitable zone, but there is nothing remotely habitable about this world. The surface of PSR B1257+12c likely experiences temperature extremes that would make even Venus seem temperate by comparison. One side of the planet probably faces the pulsar at all times due to tidal locking, creating a hemisphere that is constantly bombarded with radiation and heated to temperatures that could melt rock. possibly exceeding 1,500 degrees Celsius. The far side, perpetually facing away from the pulsar, might be hundreds of degrees below zero, creating temperature differentials that would generate storms of unimaginable ferocity. But the heat is perhaps the least of concerns for this tortured world. The regular pulses of radiation from the pulsar would sterilize any surface life within seconds. The radiation would be so intense that it would not only kill living organisms, but would also break down organic molecules themselves. This is radiation at a level that doesn't just damage DNA, it shreds the very chemical bonds that hold matter together. If a human could somehow stand on the surface of this planet, protected by some theoretical super-advanced spacesuit, they would experience the pulsar's rotation as a devastating lighthouse effect. Every third of a second, a blast of radiation would sweep across the sky, bright enough to be visible even during what passes for day on this world. The ground itself would likely glow with absorbed radiation, creating an alien landscape that pulses with deadly energy in sync with the pulsar's rotation. The gravitational forces at work would create additional nightmares. The pulsar's intense gravity would pull on the planet, creating tidal forces far more extreme than what the Moon exerts on Earth's oceans. If PSR B1257 plus 12C has any form of molten material in its interior, which is likely given the heat and radiation it endures, then its entire surface could flex and bulge with each orbit, creating a world where the ground itself breathes like a living thing, rising and falling by meters or even kilometers. This constant tidal kneading would generate enough frictional heat to melt rock, potentially creating a surface of roiling magma oceans dotted with islands of slightly cooler, semi-solid material. Volcanoes would not be discrete features, but rather the planet's default state, a world constantly turning itself inside out under the gravitational torture of its pulsar host. The magnetic environment around the pulsar would create additional horrors. Pulsars generate magnetic fields trillions of times stronger than Earth's, capable of distorting the electron clouds around atoms and altering how chemistry itself works. In the strongest magnetic regions near the pulsar, atoms would be stretched into long, thin cylinders rather than their normal spherical shapes, creating forms of matter that simply cannot exist on Earth. While PSR B1257 plus 12C orbits a bit farther out, where these extreme magnetic effects would be somewhat diminished, its environment would still be dominated by magnetic fields strong enough to tear apart any conventional spacecraft. These fields would interact with any conductive materials on the planet's surface, generating electrical currents and additional heating. Metallic elements might be heated not just by radiation, but by induction, similar to how an induction stove works, but on a planetary scale. Perhaps the strangest aspect of this world is its sky. Instead of our familiar sun, the residents of this planet, if any could somehow exist, would see a tiny, incredibly bright point of light. The pulsar itself is only about 20 kilometers across, appearing as little more than a dazzling, pulsing star. But despite its small size, this stellar remnant dominates the environment completely, spinning over 160 times per minute and sweeping its deadly beams across the planet with clock-like precision. The space around the pulsar would likely be filled with debris, remnants of the supernova that created it, possibly the shredded remains of companion stars or other planets. This debris, constantly bombarded by radiation, might glow with an eerie light, creating a nebula-like display surrounding the central pulsar. Rather than our familiar blue sky or night's darkness, this planet's atmosphere, if it retains one at all, would likely be a swirling, glowing canvas of energized particles and radiation effects. What might the composition of such a planet be? Given its formation history, PSR B1257 plus 12C is likely rich in heavy elements, the kinds of materials created in the explosive death of a massive star. Gold, platinum, uranium, and other elements rare on Earth might be commonplace on this world. The planet's core could contain exotic forms of matter created under the extreme pressures of the supernova explosion, potentially potentially including ultra-dense states that blur the line between normal matter and something more exotic. The radiation environment would transmute elements over time, turning one element into another through nuclear reactions occurring right on the planet's surface, a form of natural alchemy driven by the pulsar's relentless energy output. Areas exposed to the direct beams of the pulsar might undergo different chemical evolutions than regions receiving less direct radiation, creating a patchwork of exotic compositions across the surface. The question that haunts astronomers isn't just how this planet came to exist, but how it continues to exist. The relentless beating it takes from the pulsar should, by all rights, have evaporated it long ago, stripped away any atmosphere, eroded its surface, and potentially even fragmented it entirely. The fact that it endures suggests either that it formed relatively recently in astronomical terms, or that it possesses some extraordinary resilience we don't yet understand. Could life exist on such a world? The instinctive answer is an emphatic no. The radiation levels alone would destroy any life form similar to those on Earth instantly. But the universe has repeatedly shown us that life can adapt to environments we once thought completely inhospitable. Earth has extremophile organisms that can survive radiation levels thousands of times what would kill a human. While even these hardy organisms would likely perish on PSR B 1257 plus 12c, we cannot completely rule out the possibility of life evolving under such extreme conditions. If life did somehow gain a foothold on this radiation-blasted world, it would need to be radically different from anything we know. Perhaps it would use the pulsar's energy directly, evolving cellular mechanisms to harness the radiation rather than being damaged by it. Such organisms might treat the pulsar's regular pulses as we treat sunlight, a necessary energy source rather than a deadly hazard. They might exist in deep subsurface environments, using the planet's crust as a radiation shield while tapping into the geothermal energy generated by the pulsar's tidal forces. Or perhaps life might exist, not as discrete organisms, but as patterns in the flowing magma or in the electrically charged atmosphere. Information-carrying systems more akin to computer programs than biological life as we understand it. In an environment where conventional chemistry is constantly disrupted by radiation and magnetic fields, life might evolve along entirely different principles than the carbon-based biochemistry we're familiar with. But such speculation borders on science fiction. The more sobering reality is that PSR B 1257 plus 12c represents a class of planets that, while technically within their star's habitable zone in terms of distance, are about as inhospitable to life as any environment could possibly be. What makes this planet particularly significant to astronomers isn't just its extreme environment, but its place in history. When it was discovered along with two sibling planets in 1992 by astronomers Alexander Wolszczan and Dale Frail using the Arecibo radio telescope in Puerto Rico, it represented the first confirmed planets discovered outside our solar system. These weren't the kind of planets anyone expected to find first, worlds orbiting a normal, stable star like our Sun. Instead, our first glimpse of exoplanets came from one of the most extreme environments in the universe, a stark reminder that the cosmos rarely conforms to our expectations. The discovery of the PSR B 1257 plus 12c system also forced astronomers to reconsider their theories of planet formation. Prior to this finding, the conventional wisdom held that planets could only form around main sequence stars from protoplanetary disks. The existence of planets around a pulsar required new theories. Either planets could somehow survive their star's supernova explosion, which seems unlikely, or they could form from the debris afterward in a kind of cosmic recycling process. Today, we know of several other pulsar planets, but they remain rare compared to the thousands of worlds discovered around normal stars. This rarity might reflect the genuinely hostile nature of pulsars as host stars, or it might simply be a result of the difficulty in detecting planets around these exotic stellar remnants. Either way, PSR B 1257 plus 12c stands as a pioneer. the first glimpse of a planetary system beyond our own, and a sobering reminder of the extreme environments that exist in our universe. In a cosmic perspective, pulsar planets like PSR B1257 plus 12c represent the ultimate survivors. Worlds that exist in environments we can barely imagine, enduring conditions that seem incompatible with the very concept of a planet as we understand it. They are astronomical anomalies, planetary phoenixes born from the ashes of stellar destruction, enduring what should be unsurvivable. These worlds also offer a glimpse of the possible far future of our own solar system. While our sun isn't massive enough to become a pulsar, it will eventually become a red giant and then a white dwarf. More massive stars in the universe will follow the path to supernova and potentially pulsar formation. Any planets that form around these stellar remnants will endure conditions similar to PSR B1257 plus 12c. The universe is estimated to contain about 1 billion pulsars in our galaxy alone, though only a small fraction are currently known to us. If even a small percentage of these stellar remnants host planets, there could be millions of worlds like PSR B1257 plus 12c throughout the Milky Way. Millions of radiation-blasted super-Earths orbiting the rapidly spinning corpses of once mighty stars. This perspective gives us a new appreciation for the relative tranquility of our own solar system. Earth orbits a stable, middle-aged star that provides consistent energy without deadly radiation pulses or extreme magnetic fields. Our planet is shielded by a magnetic field that, while modest compared to a pulsar's, is strong enough to deflect much of the harmful radiation from our sun. We exist in a cosmic safe haven, a quiet suburb of the Milky Way, far from the extreme environments that dominate much of the universe. The study of worlds like PSR B1257 plus 12c helps us understand not just the diversity of planetary environments, but also the extremes of physics itself. These worlds serve as natural laboratories for testing theories about matter, radiation, and planetary evolution under conditions we could never replicate on Earth. They remind us that the universe is not just stranger than we imagine, but stranger than we can imagine. As our detection technologies improve, we may discover even more extreme planetary environments, worlds orbiting black holes, planets caught in the crossfire of colliding galaxies, or rogue planets drifting through the intergalactic void. Each will tell us something new about the resilience of planetary bodies and the diversity of environments that exist in our universe. But for now, PSR B1257 plus 12c remains one of the most hostile known worlds, a planet perpetually bathed in the wrath of a pulsar, enduring conditions that defy our understanding of what a planet can withstand. It stands as both a scientific curiosity and a cosmic warning, a reminder that not all worlds are oases of habitability. Some are more akin to cosmic torture chambers, where the very laws of physics seem bent on making planetary existence as challenging as possible. In the grand tapestry of exoplanets, PSR B1257 plus 12c represents the extreme edge of what we might even consider a planet. A world so hostile, so battered by the remnants of its parent star, that its very existence challenges our understanding of cosmic resilience. It is a world of perpetual punishment, a planet in purgatory, forever locked in the deadly embrace of a stellar corpse whose energy output is now directed not at nurturing life, but at tormenting its planetary offspring with relentless radiation. And yet, there it remains, a super-Earth-sized world, stubbornly orbiting its pulsar, defying expectations by its continued existence. In a universe full of wonders and horrors, PSR B1257 plus 12c stands as a testament to the unexpected tenacity of planets, surviving in an environment designed for destruction. It reminds us that in space, the improbable is merely unlikely, not impossible, and that worlds can exist in environments so extreme that they stretch the very definition of what it means to be a planet. Kepler 22b, a possible false Earth, In the search for habitable worlds beyond our solar system, few planets have generated as much initial excitement or subsequent disappointment as Kepler-22b. When NASA first announced its discovery in December 2011, it was heralded as a breakthrough, the first confirmed planet orbiting in the habitable zone of a Sun-like star. Headlines around the world proclaimed that we had found Earth's twin, a potential paradise world where liquid water could flow and life might flourish. But as is often the case in astronomy, the truth proved far more complex and potentially much darker. Located approximately 620 light-years away in the constellation of Cygnus, Kepler-22b was discovered by NASA's Kepler Space Telescope, a spacecraft designed specifically to find Earth-sized planets around other stars. The planet orbits Kepler-22, a star remarkably similar to our Sun, but slightly smaller and cooler, classified as a G-type main sequence star. At first glance, this system seemed like an ideal place to find a truly Earth-like world. The initial data was promising. Here was a planet, about 2.4 times the radius of Earth, orbiting its star at just the right distance to maintain temperatures suitable for liquid water on its surface. Its orbit of 290 days was remarkably close to Earth's 365-day year. For scientists searching for habitable exoplanets, Kepler-22b checked many of the right boxes. It was, they thought, a potential Goldilocks planet, not too hot, not too cold, but just right. The scientific community and the public alike embraced this promising new world. Artists' impressions depicted a blue planet with swirling white clouds, continents dotted with forests, and vast oceans glistening under the light of its sun. Kepler-22b became the poster child for habitable exoplanets, a symbol of hope that we weren't alone in the universe. Some even speculated about future interstellar missions, calculating how long it would take our fastest spacecraft to reach this tantalizing world. But science progresses through skepticism and further investigation, not through hope and artistic renderings. As astronomers continued to study Kepler-22b, a very different picture began to emerge, one far less hospitable than initially imagined. The first issue was the planet's size. With a radius approximately 2.4 times that of Earth, Kepler-22b is significantly larger than our home world. While this doesn't automatically rule out habitability, it raises important questions about the planet's composition and surface conditions. A planet of this size could be a rocky super-Earth, but it could just as easily be a mini Neptune, a world with a solid core surrounded by a thick envelope of hydrogen and helium gases with no solid surface at all. As detection and analysis techniques improved, scientists began to lean toward the latter interpretation. Rather than a larger version of Earth, Kepler-22b started to look more like a scaled-down version of Neptune or Uranus, gas-rich worlds where no solid surface exists for oceans to form or life to evolve as we know it. If this is indeed the case, then the habitable zone positioning becomes almost irrelevant. A gas planet without a solid surface cannot host life as we understand it, regardless of its temperature. The second major concern emerged from more precise measurements of the planet's orbit and the energy it receives from its star. While Kepler-22b does orbit in what astronomers technically define as the habitable zone, it's positioned near the inner edge of this region. This means it likely receives significantly more stellar energy than Earth does from the Sun, possibly enough to trigger a runaway greenhouse effect, similar to what we observe on Venus. On Venus, this process created an environment with surface temperatures hot enough to melt lead, around 475 degrees Celsius, and an atmosphere so thick and toxic that it would crush and poison a human instantaneously. If Kepler-22b experienced a similar fate, its surface, if it has one, could be a hellish landscape of molten rock under a choking blanket of superheated carbon dioxide and sulfuric acid. The third problem came from our developing understanding of stars similar to Kepler-22. While initially classified as very sun-like, more detailed observations revealed that Kepler-22 is more active than our relatively placid Sun, producing more frequent and intense stellar flares. For a planet located closer to its star than Earth is to the Sun, these flares could be catastrophic, stripping away its atmosphere over billions of years or sterilizing its surface with repeated bursts of radiation. As if these concerns weren't enough, further analysis of the Kepler data and follow-up observations began to cast doubt on the planet's very nature. Some researchers suggested that Kepler-22b might not even be a planet at all, at least not in the way we initially thought. It could be a false positive, a misinterpreted signal caused by stellar activity or instrumental artifacts. Others proposed that while the planet does exist, its size and mass measurements might be significantly different from initial estimates, potentially placing it firmly in the category of uninhabitable gas giants. The story of Kepler-22b represents a common narrative in exoplanet research: initial excitement about a potentially habitable world, followed by the sobering reality of more detailed observations. But there's something particularly unsettling about this pattern, a psychological horror that goes beyond the physical hostility of worlds like Venus or the gas giants in our solar system. The true terror of Kepler-22b lies in the false hope it represents. Imagine, for a moment, the psychological impact on future human explorers who might one day travel to this distant world, having spent generations on a journey spanning hundreds of light years, only to find not the promised Earth-like paradise, but an uninhabitable gas giant with no solid surface to land on. Or worse, a Venus-like inferno where their spacecraft would be crushed and melted within minutes of entry. This scenario is not merely a science fiction thought experiment, but a genuine concern for long-term human space exploration. As we develop more advanced telescopes and detection methods, we must be extremely careful about characterizing exoplanets, especially those we might one day consider as destinations. False positives or overly optimistic interpretations could literally lead humanity down a path to doom. The uncertainty surrounding Kepler-22b also highlights a broader philosophical horror about our place in the cosmos. If a planet that initially seemed so promising could turn out to be uninhabitable, what does this say about the prevalence of truly Earth-like worlds? Are we searching for something vanishingly rare or even unique? Is Earth not just special but possibly singular, a cosmic accident never to be repeated elsewhere in the galaxy? Scientists now estimate that the Milky Way contains billions of planets orbiting in the habitable zones of their stars. But as the case of Kepler-22b demonstrates, positioning alone is no guarantee of habitability. A truly Earth-like planet requires the right size, composition, atmosphere, magnetic field, and stable star, a combination of factors that might be exceedingly rare in the universe. The concept of a false Earth, a world that from a distance appears habitable but up close reveals itself to be deadly, creates a new category of cosmic horror. Unlike the obvious hellscapes of planets with molten metal rain or crushing pressures, these imposter worlds offer false hope, a cosmic mirage that could lure future human explorers to their doom. Beyond the physical dangers, there's something deeply unsettling about the uncertainty itself. Despite our most advanced telescopes and analysis techniques, we still cannot definitively determine the nature of Kepler-22b. It exists in a state of ambiguity, potentially habitable, potentially deadly, its true nature hidden from us by the vast gulfs of interstellar space. This ambiguity extends to many of the exoplanets we've discovered to date. We assign them categories and characteristics based on limited data, but the reality could be wildly different from our models and interpretations. The universe may be full of false Earths, planets that appear promising from hundreds of light years away, but harbor conditions utterly hostile to human life. Consider the implications for the search for extraterrestrial intelligence. If truly Earth-like planets are rare, then intelligent life might be correspondingly uncommon. Perhaps technological civilizations capable of interstellar communication or travel are so distant from one another in both space and time that they never make contact. The false promise of worlds like Kepler-22b might be mirrored in the false promise of cosmic companionship. Other intelligent species might exist, but we may never find them or be found by them. What makes the case of Kepler-22b particularly disquieting is that it was discovered by the Kepler mission, one of our most successful planet-hunting endeavors. Named after the German astronomer Johannes Kepler, whose laws of planetary motion revolutionized our understanding of the solar system, the Kepler Space Telescope operated from 2009 to 2018, discovering over 2,600 confirmed exoplanets, more than half of all known exoplanets at the time of its retirement. If one of the poster children for habitable planets from this groundbreaking mission could be so thoroughly mischaracterized, what does this say about our other discoveries? How many more false Earths might be lurking in our catalogues of supposedly habitable worlds? The case of Kepler-22b forces us to confront the limitations of our observational capabilities and the dangers of extrapolating too much from too little data. The ultimate horror of Kepler-22b is not what we know about it, but what we don't know, and may never know without sending a probe or spacecraft to investigate directly. Such a mission would take centuries with our current technology, by which time the humans who launched it would be long dead. This creates an almost existential dread. We can see these distant worlds, we can wonder about them, but we may never truly know them in any meaningful sense. This uncertainty extends beyond Kepler-22b to most of the exoplanets we've discovered. We assign them names, create artistic renderings, and speculate about their potential for habitability, but they remain fundamentally unknowable with our current technology. They exist as both data points and mysteries, scientific objects and philosophical puzzles, potential futures and potential dead ends. For astronomers and astrobiologists, the case of Kepler-22b serves as a humbling reminder of the complexity of planetary science and the dangers of premature conclusions. What initially seemed like a straightforward discovery, a planet in the habitable zone of a sun-like star, has evolved into a cautionary tale about the limitations of remote sensing and the ambiguity of astronomical data. The lessons learned from Kepler-22b have influenced how scientists approach new exoplanet discoveries. There's now greater emphasis on obtaining multiple lines of evidence before making claims about habitability, and more nuanced discussions of what constitutes a truly Earth-like world. The initial excitement about finding a potential twin to our planet has been replaced by a more mature, measured approach to characterizing alien worlds. This more cautious approach is evident in how scientists discuss more recent discoveries, such as the TRAPPIST-1 system or the planets orbiting Proxima Centauri. While these worlds orbit in the habitable zones of their stars, researchers are careful to emphasize the many factors beyond orbital distance that determine true habitability. There's a deeper psychological horror to be found in the story of Kepler-22b, one that touches on our fundamental desire to find another Earth, another home among the stars. As a species, we've long looked to the heavens and wondered if there might be other worlds like ours, other havens for life in the cosmic wilderness. The possibility that such worlds might be extraordinarily rare, or that we might be unable to distinguish the truly habitable from the merely habitable seeming, strikes at the heart of our cosmic hopes. If most or all of the supposedly habitable exoplanets we've discovered turn out to be false Earths, worlds that from a distance appear promising but up close would prove deadly, then humanity's long-term future becomes more precarious. If Earth is not merely special, but potentially unique in its perfect combination of life-supporting characteristics, then preserving our home planet becomes not just important, but essential for the survival of life as we know it. The scientific community has not given up on Kepler-22b entirely. Future observatories, such as the James Webb Space Telescope and its successors, may provide more detailed information about the planet's atmosphere, if it has one, and composition. Perhaps we'll discover that our more pessimistic reassessments were wrong, and Kepler-22b is indeed a potentially habitable world, or perhaps we'll confirm its uninhabitable nature, closing the book on what once seemed like a promising chapter in exoplanet research. Either way, the case of Kepler-22b will remain a pivotal moment in our quest to find other habitable worlds, a reminder that in astronomy, as in all sciences, initial conclusions must be held lightly, subject to revision as more data becomes available. The universe rarely conforms to our hopes or expectations, and worlds that at first glance seem familiar may, upon closer inspection, prove utterly alien. For now, Kepler-22b remains in a state of scientific limbo, neither confirmed as habitable nor definitively ruled out, a Schrödinger's planet both dead and alive in our scientific models. It orbits its star every 290 days, oblivious to our changing perceptions of it, neither knowing nor caring whether we classify it as a potential new Earth or a false hope in the cosmic wilderness. This uncertainty itself is perhaps the most honest representation of our relationship with exoplanets. Despite our advanced technology and sophisticated models, we remain distant observers, piecing together fragments of data into narratives that may or may not reflect reality. The true nature of worlds like Kepler-22b may remain hidden from us for generations to come, their surfaces, if they have them, untouched by human observation, their atmospheres, if they exist, unstudied by our instruments. In this ambiguity lies both the frustration and the wonder of astronomy. We can see farther than any previous generation of humans, detecting planets orbiting stars hundreds of light years away. Yet we remain fundamentally limited in how much we can know about these distant worlds. They are simultaneously discovered and undiscovered, known and unknown, classified yet mysterious. Perhaps the most profound horror of Kepler-22b is not that it might be uninhabitable, but that it forces us to confront the vast gaps in our knowledge and the limitations of our perception. In our quest to find other Earths, we may be like ancient mariners, navigating by stars they could see but never reach, guided by maps that contain as much speculation as fact, searching for islands that may exist only in their hopes and dreams. And yet, we continue the search, refining our instruments and methods, learning from each discovery and disappointment. The story of Kepler-22b is not just about one potentially mischaracterized planet, but about humanity's enduring quest to understand our place in the cosmos and to find other havens for life among the stars. Whether this particular world turns out to be habitable or hostile, the journey of discovery it has prompted remains valuable, a testament to our curiosity and our determination to understand the universe, even when it refuses to conform to our hopes and expectations. In the vast emptiness between stars, far from the warming glow of any sun, drift some of the most mysterious and haunting objects in our universe, rogue planets. These are worlds untethered to any star, cosmic orphans cast adrift to wander the interstellar void for eternity. Unlike every planet in our solar system, which follows a predictable orbit around our sun, rogue planets hurtle through the galaxy alone, condemned to an endless night that makes even the darkest corners of our solar system seem bright by comparison. The very concept of a planet without a star challenges our fundamental understanding of what a planet is. From our earliest days of astronomy, planets were defined by their relationship to stars, worlds that orbit a central luminous body. The word planet itself comes from the ancient Greek term for wanderer, referring to how these objects appeared to move against the fixed background of stars in the night sky. But rogue planets truly embody this original meaning. They are wanderers in the most literal sense, drifting wherever gravitational forces push and pull them across the cosmic sea. What makes rogue planets particularly terrifying is not just their isolation, but their prevalence. Astronomers now believe these nomadic worlds might outnumber stars in our galaxy. Recent studies suggest there could be anywhere from hundreds of billions to trillions of rogue planets drifting through the Milky Way alone. This means that most planets in our galaxy might not orbit stars at all, but instead drift in perpetual darkness, invisible to us except through the most sophisticated detection methods. But how do these cosmic orphans come to exist? The formation of rogue planets represents some of the most violent processes in planetary astronomy. Some are born as normal planets around stars, only to be violently ejected from their solar systems. This ejection can occur during the chaotic early formation of a planetary system, when gravitational interactions between newly formed planets can send worlds careening into interstellar space. Imagine the catastrophe: a planetary collision or near miss so powerful that it launches an entire world out of its solar system, breaking the gravitational bonds that anchored it to its parent star. Other rogue planets may form in isolation from the same molecular clouds that create stars and planetary systems, but without gathering enough mass to ignite nuclear fusion and become stars themselves. These are, in a sense, failed stars. Objects massive enough to be considered brown dwarfs or gas giant planets, but too small to shine with their own light. They emerge from stellar nurseries alone, never knowing the orbit of a parent star, drifting from birth into the endless night. Life on a rogue planet would face challenges beyond anything we can easily imagine. Without a star to provide energy, the surface temperature of these wandering worlds would approach absolute zero, negative 273.15 degrees Celsius, the coldest temperature physically possible. At these temperatures, atmospheres would freeze solid, forming layers of frozen gases on the planetary surface. Any oceans would be frozen to their depths, harder than concrete. The only light would come from the distant stars, too faint to do more than provide the faintest illumination, and perhaps from auroras generated by the planet's magnetic field interacting with charged particles in interstellar space. Yet, remarkably, some scientists believe certain rogue planets might not be entirely dead worlds. Those that formed in stellar systems before being ejected might retain significant internal heat, particularly massive gas giants similar to Jupiter. Jupiter actually generates more internal heat than it receives from the Sun, a product of its ongoing gravitational contraction and potentially the separation of helium from hydrogen in its interior. A rogue gas giant might maintain this internal heat for billions of years after being cast into interstellar space. Even more intriguing are rocky worlds large enough to retain substantial geothermal heat and possessing thick insulating atmospheres or ice sheets. These layers could trap heat from radioactive decay in the planet's core, potentially creating subsurface oceans of liquid water. Remarkably, these hidden oceans might remain liquid for billions of years, sustained by the planet's internal heat long after its exile from its parent star. Imagine a vast, liquid water ocean encased between a frozen surface and a rocky seabed. Utterly isolated from the cosmos by kilometers of ever-coming would challenge our deepest psychological adaptations. Perhaps the most disturbing aspect of rogue planets is the possibility that Earth itself could one day become one. While extremely unlikely in our Sun's lifetime, catastrophic events such as a close encounter with another star could potentially disrupt planetary orbits enough to send Earth drifting away from the Sun. If this happened, the consequences would unfold with terrifying rapidity. Within a week of being ejected from the solar system, Earth's average surface temperature would drop below freezing. Within months, the oceans would begin to freeze, starting at the poles and working toward the equator. Within a year, the atmosphere would begin to condense and fall as exotic snow, first carbon dioxide, then oxygen and nitrogen. Within decades, the planet would be encased in ice, with only geothermal features providing any hint of the once vibrant world beneath. Most surface life would perish within the first year, as photosynthesis ceased and temperatures plummeted. Some human populations might survive for decades using geothermal energy, nuclear power, and hydroponics. But eventually, these too would fail as equipment broke down and resources dwindled. The last vestiges of humanity might gather around deep ocean vents, trying to establish colonies mimicking the chemosynthetic ecosystems that might be the only long-term survivors on a rogue Earth. Eventually, perhaps after millions of years, our once-living world would resemble the other rogue planets, a frozen ball drifting through the cosmic void, its surface scoured by interstellar dust, its former civilization preserved perfectly in the deep freeze of space, waiting for a discovery that would likely never come. Detecting rogue planets remains one of astronomy's greatest challenges. Unlike stars or even normal planets, which can be observed directly or indirectly through their interactions with their stars, rogue planets emit almost no detectable signature. They're too cold to emit significant infrared radiation, reflect no starlight, and only rarely pass directly between us and a background star to create detectable gravitational lensing effects. This observational challenge means our understanding of rogue planets remains largely theoretical. We don't know their typical sizes, compositions, or origins with any certainty. We can't tell if they predominantly form as ejected planets from star systems or as failed stars in their own right. We can't determine if they typically retain atmospheres or if these are entirely frozen out. The populations of potential life-harboring worlds with subsurface oceans remain entirely speculative. What makes rogue planets particularly haunting is the possibility that some might have once harbored thriving biospheres before being ejected from their solar systems. Imagine a world like Earth, teeming with life, perhaps even intelligent civilization, suddenly torn from its sun and cast into the interstellar void. The apocalypse would unfold slowly enough for the inhabitants to understand exactly what was happening, but too quickly for any meaningful adaptation. Such a civilization might document their world's descent into eternal winter, recording the final sunset, the gradual darkening of the skies as the star shrinks to a point, and then to nothing but another distant light among many. They would measure the falling temperatures, the failing ecosystems, the desperate attempts to survive. Their final messages would mark the end, not just of their species, but of an entire biosphere, a planetary apocalypse of cosmic proportions. While such a scenario remains in the realm of science fiction for civilized worlds, it has almost certainly happened countless times to lifeless planets throughout the galaxy's history. Every star system forms through chaotic processes, and many planets are ejected during these formative stages. Our own solar system likely lost several planetary embryos during its formation, casting them into interstellar space before they could develop into proper planets in stable orbits. Some astronomers speculate that a special class of rogue planets might actually be habitable despite their sunless state. These would be worlds with thick hydrogen atmospheres, much thicker than Earth's atmosphere, creating enough greenhouse warming and pressure to maintain surface temperatures above the freezing point of water. While very different from Earth, such worlds could potentially support liquid water on their surfaces for billions of years after ejection from their parent stars. The physics is surprisingly sound. Molecular hydrogen is an excellent insulator, and enough of it could trap geothermal heat effectively. The pressure of such a massive atmosphere would also help keep water liquid at temperatures that would otherwise cause it to freeze. These hydrogen worlds would still be dark, with any light coming solely from auroras and perhaps bioluminescent life, but they wouldn't be frozen solid like most rogue planets. If such worlds exist, and theoretical models suggest they should, they would represent perhaps the most alien habitable environments in the universe. Their perpetual darkness would eliminate photosynthesis as we know it, forcing life to evolve along entirely different lines. Their stable temperatures and isolation from cosmic influences like solar flares, asteroid impacts, and gamma-ray bursts might actually make them more stable environments for life than planets orbiting stars. This raises a disturbing possibility for astrobiologists. What if most of the life in the universe exists not on planets orbiting stars, as we've always assumed, but on rogue planets drifting through the darkness between them? Our search for extraterrestrial life has focused almost exclusively on star systems, but if habitable rogue planets outnumber habitable orbiting planets, we might be looking in entirely the wrong places. Such life would never develop technology as we understand it. Without easily accessible energy from a star, without fire, impossible in a hydrogen atmosphere, without day-night cycles to evolve circadian rhythms, and without stars visible in their sky to inspire astronomy, intelligent life on rogue planets would develop along entirely different trajectories than humanity. They would never know their place in the cosmos, never develop astronomy, never realize they are drifting through space rather than sitting at the center of a dark universe. The concept of rogue planets challenges our anthropocentric view of habitability and life. We evolved on a planet bathed in starlight, with abundant energy from the sun driving our biosphere. Our definition of habitability centers on this experience. Planets at the right distance from their stars to maintain liquid water. But the universe may have many more pathways to habitability than we've considered, including worlds that drift alone through the cosmic void. The detection of rogue planets represents one of the frontiers of modern astronomy. Future space telescopes and survey methods may eventually reveal these invisible wanderers in greater numbers, helping us understand their prevalence and characteristics. Ground-based surveys using gravitational microlensing have already found evidence for rogue planet populations, but these detections remain rare and limited. Perhaps the most profound philosophical implication of rogue planets is what they tell us about the nature of our universe. We often view planets as being defined by their relationship to stars, as objects in orbit, components of solar systems, places warmed and lit by their suns. But rogue planets remind us that most of the universe is cold, dark, and isolated. Most of space is empty void. Most planets may drift alone rather than orbit stars. Most of existence may be solitary rather than connected. In this cosmic perspective, Earth seems even more precious, not just as a habitable world, but as a planet blessed with a stable orbit around a stable star. Our planet's relationship with the Sun isn't just what makes life possible, it's what connects us to the cosmic neighborhood, what gives us day and night, seasons and cycles, the very rhythm of existence that we take for granted. Rogue planets have none of this. They are truly alone in a way that challenges our very concept of what a world can be. As our understanding of rogue planets improves, they may help us answer some of the most fundamental questions in planetary science. How common are planets throughout the galaxy? How often are they ejected from their solar systems? Could life exist in the absence of a parent star? Are most habitable worlds orbiting stars or drifting alone through the void? The answers to these questions will shape our understanding, not just of planetary science, but of life's place in the cosmos. If habitable rogue planets are common, life may be far more widespread than we've imagined, but also far more isolated, evolving on worlds that will never know contact with others, developing in darkness and solitude, in the vast emptiness between the stars. In the end, rogue planets represent both the terror and the wonder of our universe. Worlds of perpetual night drifting silently through the void, isolated beyond human comprehension, yet potentially harboring their own forms of life adapted to conditions we can barely imagine. They remind us that the cosmos is not just stranger than we imagine, but stranger than we can imagine, filled with worlds and possibilities that challenge our most basic assumptions about what planets are and where life might exist. As you gaze at the night sky, remember that between those distant points of light drift countless invisible worlds, their surfaces locked in eternal ice, their potential subsurface oceans hidden from view, their stories untold and perhaps untellable. In the darkness between the stars lies a population of planets potentially vaster than all the worlds orbiting all the stars we can see. A dark exoplanet census ghosting through the galaxy, unknown and unknowable, except through the most fleeting glimpses of science. These are the true wanderers of the cosmos, the nomads of interstellar space, the orphans of the galactic family, rogue planets, drifting eternally through the darkness, carrying their frozen secrets through the void between the stars. In the grand theatre of cosmic horror, perhaps no fate is more terrifying than that of WASP-12b, a planet literally being devoured alive by its parent star. This is not a slow process measured in billions of years like most cosmic phenomena, but a violent, active consumption happening right now as we observe it. Located approximately 870 light-years from Earth in the constellation Auriga, this doomed world represents one of the most extreme and disturbing planetary systems ever discovered, a cosmic tragedy playing out in real time that gives astronomers nightmares and fascinates them in equal measure. WASP-12b is what astronomers call a hot Jupiter, a massive gas giant orbiting perilously close to its star. But even among hot Jupiters, which are known for their hellish conditions, WASP-12b stands out as particularly unfortunate. This world, with a mass approximately 1.4 times that of Jupiter, orbits its star at a distance of just 3.4 million kilometers, more than 20 times closer than Mercury orbits our Sun. At this tiny orbital distance, the planet completes a full orbit in just over 1 Earth day. This means that a year on WASP-12b passes in the time it takes Earth to rotate once on its axis. This proximity to its star creates conditions that are almost impossible to comprehend, and that are literally tearing the planet apart. The star at the center of this system, WASP-12, is slightly larger and more massive than our Sun, with a surface temperature of approximately 6,000 degrees Celsius. At WASP-12b's orbital distance, the star appears 60 times larger in the sky than our Sun appears from Earth. Imagine a celestial body filling nearly a third of your entire sky. Not a disk in the distance, but a looming wall of nuclear fire stretching across your horizon. The temperature on the day side of WASP-12b reaches an almost incomprehensible 2,500 degrees Celsius, hot enough to melt steel, iron, and most other metals. This extreme heat has consequences beyond just creating an inhospitable environment. It causes the planet's atmosphere to balloon outward, extending far beyond the range a similar planet in a more distant orbit would maintain. This bloated atmosphere is where the true horror of WASP-12b becomes apparent. The star's gravitational pull is literally stripping away the planet's outer layers, pulling its atmospheric material into an accretion disk around the star. Recent observations from the Hubble Space Telescope have confirmed what astronomers had long suspected. WASP-12b is being cannibalized by its parent star. Scientists estimate that the planet is losing mass at a rate of approximately 6 billion kilograms per second, a number so large it defies easy comprehension. To put this in perspective, it's equivalent to about 6,000 large aircraft carriers vaporizing every single second. Over the course of a single Earth day, WASP-12b loses mass equivalent to a small moon. This equates to the mass of Earth's entire atmosphere being stripped away in just 42,000 years, a mere eye blink in astronomical terms. The math of planetary destruction is both precise and terrifying. At current rates, the entire planet, a gas giant 1.4 times the mass of Jupiter, containing enough material to make hundreds of Earths, will be completely consumed within 10 million years. Nothing will remain except a faint enhancement of certain elements in its star's outer layers as evidence it ever existed at all. A chemical epitaph for a world completely unmade by its sun. The process of this planetary consumption is both violent and eerily beautiful. The material pulled from WASP-12b forms a long comet-like tail trailing behind the planet in its orbit. This stream of ex-planetary material eventually feeds into an accretion disk around the star, creating a cosmic Ouroboros, a star eating its own planetary offspring, incorporating the very material that formed from its stellar nebula billions of years earlier. Observed in ultraviolet light, this tail of escaping planetary material stretches for thousands of kilometers behind the planet, like a ghost trail marking WASP-12b's orbital path. It's a visualization of planetary death, a time-lapse of cosmic destruction made visible to our telescopes. What makes this scenario particularly disturbing is that it represents the ultimate fate of many planets throughout the universe. While WASP-12b's situation is extreme, even by the standards of hot Jupiters, the basic process, a planet migrating inward and eventually being consumed by its star, is thought to be relatively common in planetary evolution. Astronomers believe that many star systems form planets that eventually spiral inward due to various gravitational interactions. Some are consumed early in their system's history, leaving no trace for later observers. Others, like WASP-12b, happen to exist at exactly the moment when their consumption is underway, allowing us to witness planetary destruction in real time. The mechanics of WASP-12b's destruction involve several overlapping processes, each more terrifying than the last. The first is tidal disruption. The star's massive gravitational field creates tidal forces that stretch the planet along the star-planet axis while compressing it in the perpendicular direction. These tides are similar to those the Moon creates on Earth's oceans, but magnified to an extreme degree. The difference in gravitational pull between the near and far sides of WASP-12b is so great that the planet is stretched into an egg shape rather than a sphere. This distortion generates massive amounts of frictional heating within the planet, further destabilizing its structure and contributing to its bloated size. The planet is being kneaded like cosmic dough, generating heat that helps drive its atmosphere outward toward the waiting gravity of its star. The second destructive process is atmospheric escape. The extreme heat from the star energizes the atoms and molecules in WASP-12b's upper atmosphere, causing them to move so rapidly that they can escape the planet's gravity. This is similar to how Earth loses a small amount of hydrogen from the top of our atmosphere, but scaled up to catastrophic levels. On WASP-12b, this atmospheric escape is so extreme that the planet has lost its characteristically round shape. Instead, it resembles something closer to a teardrop or a comet, with its atmosphere stretching away from the star, only to be captured by the star's greater gravitational pull and drawn into a deadly spiral. The third mechanism of destruction is photoevaporation. The star's intense ultraviolet radiation literally blasts away the planet's outer layers, ionizing atoms and allowing them to be swept away by the stellar wind. This process is particularly effective at removing lighter elements like hydrogen and helium, precisely the elements that make up most of a gas giant's mass. The combination of these processes creates a planetary system that more closely resembles a crime scene than the stable, well-ordered solar system we're familiar with. WASP-12b isn't just a hot planet. It's a victim of cosmic violence, a world caught in the act of being dismembered by the very star it orbits. Perhaps the most distressing aspect of WASP-12b's fate is its absolute inevitability. From the moment the planet migrated or formed too close to its star, its doom was sealed with the certainty of a mathematical equation. There is no escape, no possible intervention that could save it, no technological solution that even an advanced civilization could implement to halt the destruction. The gravitational forces at work are simply too immense to counteract. The laws of physics themselves have condemned this world to a slow death, played out over millions of years as it gradually spirals closer to its stellar executioner. It's a perfect demonstration of deterministic physics on a planetary scale. Once certain conditions are established, the outcome becomes unavoidable. WASP-12b is not merely dying, it is experiencing the only fate possible given its position and composition, a cosmological tragedy written in the language of orbital mechanics and thermodynamics. The planet's orbit is already so close to its star that it experiences significant tidal braking, gradually slowing it down and causing it to spiral inward. With each passing millennium, WASP-12b moves slightly closer to its star, experiencing even greater tidal forces, losing its atmosphere at an even faster rate, locked in a death spiral that can have only one outcome. This raises a disturbing question for planetary scientists. How many planets meet similar fates? Our own solar system seems remarkably stable, with planets in nearly circular orbits at comfortable distances from the Sun. But this may not be the norm throughout the galaxy. Many planetary systems may be far more dynamic and violent, with worlds migrating inward or outward, being ejected into interstellar space, or like WASP-12b, being consumed by their stars. We know from exoplanet surveys that hot Jupiters like WASP-12b are relatively common, making up about 1% of all known exoplanets. While not all of these worlds are currently being torn apart like WASP-12b, many may face similar fates in the future. Their very existence so close to their stars suggests that planetary migration, worlds forming farther out and then moving inward, is a common process in planetary system evolution. If planetary migration and stellar consumption are common, then the galaxy may be filled with worlds in various stages of destruction. Some may be like WASP-12b, actively losing their atmospheres to their stars. Others may be even closer to their final moments. reduced to dense cores that will soon plunge into their stellar surfaces. Still others may have already been consumed, their former existence detectable only through unusual elemental abundances in their stars' atmospheres. This cosmic recycling process, planets forming from stellar material only to eventually be reabsorbed by their stars, creates a disturbing cycle of creation and destruction. The very atoms that make up a consumed planet will eventually be redistributed when its star dies, potentially forming new planets around new stars. Matter is neither created nor destroyed in this process, merely reformed and repurposed in an endless cycle. For humans contemplating such systems, there's a philosophical horror beyond the physical destruction. WASP-12b represents impermanence on a cosmic scale, a reminder that even worlds have lifespans, that the ground beneath our feet isn't eternally stable, that entire planets can be created and destroyed in the grand cycles of stellar evolution. What would it be like to witness such destruction firsthand? Imagine a hypothetical observer somehow able to survive on or near WASP-12b. They would see the star filling nearly a third of the sky, its surface a roiling sea of plasma, magnetic storms arcing across its face. The atmosphere around them would be streaming away toward the star, creating perpetual one-way winds of incredible force. Looking back along their orbit, they would see the comet-like tail of planetary material stretching into space, the literal substance of their world being pulled away into nothingness. With each orbit, completed in just over a day, they would see slightly more of their planet gone, the process of destruction measurable in real time. Such an observer would experience time very differently than we do on Earth. With orbital periods measured in hours rather than years, their entire concept of time would be compressed. 1 million orbits, roughly equivalent to 1 million Earth days, or about 3,000 years, would see noticeable changes in the planet's size and orbit. 10 million orbits would witness the complete destruction of the world. Cosmic processes that normally take billions of years would unfold in a cosmically brief eye blink. The destruction of WASP-12b also raises questions about the fate of our own planet. While Earth is in no immediate danger, our orbit is stable and the Sun is a much more sedate star than WASP-12. We know that our planet will eventually face destruction when the Sun enters its red giant phase in about 5 billion years. During this phase, the Sun will expand to hundreds of times its current size, engulfing Mercury and Venus, and possibly Earth as well. Even if our planet escapes direct consumption, the extreme heat will boil away the oceans and strip away the atmosphere, leaving Earth a scorched, barren rock, orbiting precariously close to the bloated red surface of our dying star. What we're witnessing with WASP-12b may be a preview of Earth's ultimate fate, a glimpse of cosmic processes that will eventually claim our own world. The difference is merely one of timescale and intensity. While WASP-12b is being violently torn apart over millions of years, Earth faces a slower but no less certain doom billions of years in the future. This connection between WASP-12b's current destruction and Earth's distant fate creates a sort of cosmic memento mori, a reminder of planetary mortality that transcends the human timescale. Just as individual humans must face their mortality, so too must we recognize that planets themselves are temporary structures in the cosmic landscape. The discovery and observation of WASP-12b represent a triumph of modern astronomy. The planet was first detected in 2008 by the SuperWASP, Wide-Angle Search for Planets project, a ground-based survey using small automated telescopes to detect the tiny dimming of stars when planets pass in front of them, a technique known as transit photometry. Follow-up observations by more powerful telescopes, including the Hubble Space Telescope, revealed the planet's bloated nature and the material streaming from it toward its star. These observations have allowed astronomers to study a process of planetary destruction that, until recently, existed only in theoretical models and computer simulations. WASP-12b has become one of the most studied exoplanets precisely because of its extreme conditions. It serves as a natural laboratory for testing theories of planetary structure, atmospheric escape, and star-planet interactions. Its very destruction has made it valuable to science, allowing us to witness processes that usually unfold too slowly for human observation. The planet also challenges our understanding of what planetary environments can exist. Its dayside temperature of 2,500 degrees Celsius is hot enough to break down complex molecules into their constituent atoms. At such temperatures, chemistry as we understand it breaks down, replaced by a simpler realm of atomic interactions and ionized gases. Spectroscopic observations of WASP-12b's atmosphere have detected elements like iron and magnesium in gaseous form, substances that on Earth exist primarily as solids. This creates an alien environment where metals exist as vapors in the atmosphere, potentially condensing as metallic rain on the slightly cooler night side of the planet. The extreme tidal forces WASP-12b experiences also affect its weather patterns in ways we're only beginning to understand. Unlike Jupiter, which rotates once every 10 hours, creating its characteristic banded appearance, WASP-12b is tidally locked to its star, always presenting the same face toward it. This creates a permanent hotspot on the day side and a complex pattern of winds circulating heat to the night side. Computer models suggest that winds on WASP-12b may reach speeds of thousands of kilometers per hour as they attempt to redistribute the extreme heat from the day side to the night side. The fastest tornadoes on Earth, by comparison, rarely exceed 400 kilometers per hour. These super hurricane force winds on WASP-12b would carry vaporized metals through the atmosphere, creating weather patterns unlike anything in our solar system. Storms of gaseous iron and silicate flowing around a planet being stretched and torn by tidal forces. The thermodynamic extremes create other bizarre phenomena. Where these superheated metal winds meet slightly cooler regions, they might condense into droplets, creating rain made of liquid iron and other metals falling through an atmosphere hot enough to melt steel. Lightning storms of unimaginable intensity would flash constantly through this metal-saturated atmosphere, their bolts perhaps thousands of times more powerful than those on Earth due to the excellent conductivity of the ionized metallic gases. The entire atmosphere would glow not just from reflected starlight, but from its own heat, a planetary-scale version of an iron bar heated to incandescence. The discovery of planets like WASP-12b has transformed our understanding of planetary systems, showing that they can be dynamic, violent places where worlds form, migrate, and are destroyed on timescales far shorter than the lifetime of their stars. Our own solar system, with its nearly circular orbits and relatively stable planetary positions, may be the exception rather than the rule. Many planetary systems may exist in states of slow-motion chaos, with worlds gradually spiraling inward toward consumption or outward toward ejection into interstellar space. The stable planetary arrangements we once thought typical may actually be rare, preserved only in systems that avoided the gravitational disturbances that drive planetary migration. As our observations of exoplanets continue to improve, we may discover more worlds in various stages of destruction, some just beginning the process that will eventually consume them, others in their final death spirals. Each will provide new insights into the processes shaping planetary systems throughout the galaxy. The story of WASP-12b serves as a cosmic reminder of impermanence, that even objects as massive and seemingly eternal as planets have lifespans, that the universe is in a constant state of creation and destruction, building up and tearing down on timescales that dwarf human experience, but are mere moments in cosmic time. In the end, WASP-12b isn't just a scientific curiosity or an extreme world. It's a glimpse into cosmic processes that shape the evolution of planetary systems throughout the universe. Its destruction, while tragic in human terms, is part of the natural cycle of matter in the cosmos, a cycle that will eventually claim all planets, including our own. As we gaze through our telescopes at this doomed world, slowly feeding its substance to its ravenous star, we're witnessing not just an astronomical oddity, but a fundamental truth about the universe, that nothing, not even worlds, lasts forever. In the grand cosmic scale, planets form, exist for a time, and then return their substance to the stars from which they formed. their matter recycled into new worlds in an endless cycle of cosmic renewal. This cycle of planetary birth and death is perhaps the ultimate expression of the conservation of matter and energy that underlies all of physics. The atoms that today make up WASP-12b once existed in the nebula that formed its star. Soon, astronomically speaking, they will exist within the star itself, and eventually, when that star dies, they may be scattered into space to form new planets around new stars. The planet dies, but its substance is eternal, constantly recycled through different forms across the eons. WASP-12b's fate reminds us that we exist in a dynamic, ever-changing universe where even the ground beneath our feet is temporary. A humbling perspective that places our brief human concerns in the context of cosmic time and cosmic cycles. In its destruction, this distant world teaches us something profound about the nature of existence itself. That impermanence is not just a human condition, but a universal one, applying even to the worlds that circle the stars. And perhaps most hauntingly, as we observe this planet's death throes from afar, we're reminded that somewhere in the vastness of the universe, other beings on other worlds might someday observe Earth's eventual consumption by our own expanding sun. The ultimate cosmic reminder that all things, even entire worlds, are but temporary arrangements of matter in an ever-changing cosmos. As we conclude our journey through the most terrifying planets known to science, it's worth taking a moment to reflect on what these horrifying worlds reveal about our universe and our place within it. From glass rain and molten iron showers to crushing pressures and deadly radiation, the cosmos has proven itself to be a master architect of nightmares, crafting planetary environments that defy our earthly imaginations and challenge our very understanding of what constitutes a world. The planets we've explored are extreme by human standards, but they're not anomalies or aberrations in cosmic terms. They are natural outcomes of the same physical laws that govern our own world, simply operating under different initial conditions or circumstances. The universe doesn't create these worlds to terrify us. They are merely the result of gravity, thermodynamics, chemistry, and other fundamental forces playing out across a canvas of staggering diversity and scale. Each of the planets we've explored represents an extreme version of processes that exist throughout the universe. The sideways glass rain of HD 189733b demonstrates how commonplace materials can become deadly weapons under alien conditions. The perpetual lava oceans of K2-141b reveal how radically different a planet's surface can be when locked in an extreme orbit. The iron rain of WASP-76b shows us how familiar elements behave in unfamiliar ways under extreme temperatures. Venus, our nearest planetary neighbor, reminds us that even worlds similar to Earth can become uninhabitable through runaway climate processes. The burning ice of Gliese 436b demonstrates how pressure and temperature can create states of matter that seem to defy common sense. The endless oceans of TRAPPIST-1d hint at alien ecosystems potentially evolving in isolation from any concept of land or sky. The pulsar planet PSR-B 1257+12c exists in a state of perpetual radiation bombardment that would destroy any conventional definition of habitability. Kepler-22b, once thought to be a second Earth, now stands as a cautionary tale about false hope in the search for habitable worlds. The rogue planets drifting between stars remind us that not all worlds enjoy the warming embrace of a stellar companion, and the doomed WASP-12b, literally being consumed by its star, demonstrates the impermanence of even planetary bodies on cosmic timescales. These worlds, as terrifying as they are, teach us something profound about the nature of the universe itself. They reveal that our comfortable Earth, with its moderate temperatures, breathable atmosphere, and stable orbit, is not the template for planetary existence that we once imagined it to be. Rather, Earth represents something precious and perhaps rare, a delicate balance of conditions that permit life as we know it to flourish. The deadly planets we've explored are not exceptions or aberrations. If anything, they may represent the norm, with Earth being the true cosmic outlier. For every world like ours, With its gentle rains of water and its oxygen-rich atmosphere, there may be dozens or hundreds of planets where it rains molten glass or iron, where the atmosphere would crush and poison us in seconds, or where radiation levels would destroy any Earth-like biology. This sobering reality forces us to reconsider what we mean by terms like habitable or Earth-like. The conditions we evolved to consider normal represent just a tiny island of stability in a vast sea of extreme possibilities. What we call room temperature or normal pressure are anything but normal when viewed against the backdrop of cosmic diversity. Our very definition of what constitutes a habitable environment is limited by our evolutionary history and planetary origin. The gulf between what we consider habitable and what the universe routinely produces is so vast that it can induce a kind of cosmic vertigo, a disorienting realization that our comfortable existence depends on parameters so specific, so precariously balanced, that they may be vanishingly rare among the trillions of planets that likely exist in our galaxy alone. Earth is not just rare, it may be exceptional to a degree that's difficult to fully grasp. Yet even as these deadly worlds challenge our Earth-centric perspective, they also expand our understanding of where and how life might exist in the universe. If there's one lesson that biology on Earth has taught us, it's that life is adaptable beyond our wildest expectations. Organisms on our own planet have evolved to thrive in volcanic vents, in radioactive waste, in the driest deserts, the coldest ice, and the most acidic pools, environments once thought completely hostile to life. If Earth life can adapt to such extremes, might not life evolve from scratch in environments we consider thoroughly uninhabitable? Could there be silicon-based organisms surfing the molten glass clouds of HD 1897-33b, or metallic hydrogen creatures swimming through the atmospheric oceans of gas giants? Might pressure-adapted organisms thrive in the crushing depths of water worlds, or radiation-eating microbes flourish on planets bathed in the energy of pulsars? While such possibilities remain speculative, the extreme planets we've explored force us to broaden our conception of habitability. Life may be far more common and far more diverse than our Earth-biased perspective allows us to imagine. The universe's deadliest worlds, from our human viewpoint, might harbor thriving ecosystems based on biochemistries and adaptive strategies beyond our current scientific understanding. This possibility creates a paradox for astrobiologists. The types of planets most likely to harbor familiar Earth-like life may be relatively rare, while planets with potential for exotic alien life may be abundant but difficult for us to recognize as habitable. Our search for life beyond Earth may be hampered not by our lack of living worlds, but by our limited ability to recognize life that evolved under radically different conditions than our own. Consider what we might be missing with our Earth-centric perspective. Could there be life forms that use methane as a solvent instead of water? Organisms that incorporate silicon into their biochemistry instead of carbon? Beings that process information through chemical signals rather than electrical impulses? Creatures that perceive the universe through senses so different from our own that we would struggle to recognize their intelligence? The deadly planets open these possibilities, suggesting that life as we don't know it could be thriving in environments we consider utterly hostile. Beyond their implications for astrobiology, these extreme worlds also serve as cosmic laboratories, natural experiments running at scales and under conditions impossible to replicate on Earth. By studying iron rain on WASP 76b or the glass clouds of HD 189733b, scientists can test theories about material behavior under extreme temperatures and pressures. The destruction of WASP 12b allows us to observe star-planet interactions that normally unfold too slowly to detect. Even seemingly hostile Venus provides insights into climate processes relevant to understanding Earth's future. These deadly planets also offer a humbling perspective on humanity's place in the cosmos. Our civilization exists on a remarkably benign world, protected from cosmic extremes by a fortunate combination of factors: our distance from the Sun, Earth's protective magnetic field, our atmosphere's particular composition, our planet's stable rotation, and countless other conditions we often take for granted. This cosmic perspective makes Earth seem all the more precious, an oasis of habitability in a universe dominated by extremes. The terrifying worlds we've explored are not just scientific curiosities. They're reminders of how special our home planet truly is, and why preserving its habitability should be among our highest priorities as a species. Our home planet exists in a sweet spot of cosmic parameters, not too hot, not too cold, not too massive, not too small. With just the right amount of water, the right balance of land and ocean, the perfect distance from a stable star, a protective magnetic field of just the right strength, a large moon stabilizing our axial tilt, and a position in a relatively quiet galactic neighborhood. Any significant deviation in these parameters could push Earth toward the extremes we've witnessed on other worlds, rendering it uninhabitable for creatures like ourselves. As our technology improves, we'll undoubtedly discover planets even more extreme than those we've explored in this journey. Future telescopes will resolve surface features on distant worlds, analyze their atmospheric compositions in detail, and perhaps even detect signs of life adapted to conditions we currently consider impossible. The catalogue of cosmic horrors will expand, challenging our imagination and scientific understanding in new ways. But we'll also find more worlds that resemble Earth, planets orbiting in the habitable zones of their stars, with signs of water and atmospheres that might support familiar forms of life. The search for these cosmic siblings remains one of humanity's great scientific quests, driven by the profound question of whether we are alone in the universe or part of a wider community of living worlds. The deadly planets we've explored exist in the same universe as potentially life-bearing worlds, two sides of the same cosmic coin. Together, they tell the story of planetary diversity, how the same physical laws and chemical elements that make Earth so perfectly suited to our form of life can also create environments of extraordinary hostility. This duality reminds us that the universe is neither inherently hostile nor inherently welcoming to life as we know it. Rather, it is indifferent, a vast arena of physical processes unfolding according to fundamental laws, creating environments of stunning variety across billions of worlds. Some of these environments happen to support carbon-based life like ours. Others create conditions where such life could never survive. The universe operates without intention or purpose in how it distributes these conditions. The same gravity that holds Earth in its life-sustaining orbit also creates the crushing pressures in the atmospheres of gas giants. The same stellar processes that warm our planet to comfortable temperatures also produce the deadly radiation that bathes planets orbiting pulsars. The same geological activity that recycles our atmosphere also creates the hellish volcanic landscapes of worlds like K2-141b. Beauty and horror, habitability and deadly extremes. These are not opposing forces in the cosmos, but different expressions of the same underlying physics. The true wonder of modern astronomy is that we can now detect and characterize these distant worlds, despite being bound to our own planet. Through the light gathered by our telescopes, the signals processed by our computers, and the models constructed by our scientists, we can explore places no human could ever physically visit. Worlds where it rains molten iron, where oceans of lava cover the surface, where pressures would crush us and temperatures would vaporize us in an instant. These virtual explorations of deadly worlds serve a crucial function in our development as a cosmic species. They remind us that the universe is far stranger, more extreme, and more diverse than our everyday experience suggests. They challenge us to expand our thinking beyond Earth-based assumptions, to consider physical processes and environments utterly alien to human experience. Perhaps the most profound lesson from our tour of the universe's deadliest worlds is about perspective. Earth, which we often view as fragile when considering human impacts on its ecosystems, is actually remarkably robust compared to many planets. It has maintained habitable conditions for billions of years, despite asteroid impacts, solar fluctuations, and other cosmic challenges. The stability of Earth's environment, when contrasted with the extremes we've explored, appears all the more remarkable. At the same time, the deadly planets remind us that cosmic processes operate on scales far beyond human control. We cannot tame WASP-12b's destruction or calm the glass storms of HD 189733b. These worlds follow trajectories dictated by the fundamental forces of nature, indifferent to observation or intervention. They exist not to frighten or inspire us, but simply because the physics of our universe allows, or even requires, such conditions to form. This cosmic indifference can be terrifying from a human perspective. We evolved as creatures adapted to control our immediate environment, to shape our surroundings for our benefit and safety. The deadly planets remind us that this control is both limited and local, that beyond our thin atmospheric shell lies a universe governed by forces that dwarf our capabilities and often create conditions antithetical to our existence. Yet there's something oddly comforting in this cosmic perspective as well. The same indifferent universe that creates worlds of glass rain and iron storms also created Earth, with its perfect balance of conditions for life. The same physical laws that tear WASP-12b apart also hold our planet in its life-sustaining orbit. We are not separate from these cosmic processes, but part of them, children of a universe that contains both extraordinary violence and extraordinary beauty. This perspective shifts how we might view humanity's place in the cosmos. We are not the center of creation, nor are we insignificant accidents. Rather, we are a natural outgrowth of a universe that, through its fundamental properties, creates both deadly worlds and habitable ones. Our existence isn't miraculous in a supernatural sense, but it is remarkable in a statistical one. We inhabit a planet whose parameters fall within the narrow band that permits our form of life, amid a universe that routinely produces worlds hostile to that life. As we look to the future of planetary exploration, both within our solar system and beyond, the extreme worlds we've studied will inform our understanding of what to expect. When we send probes to Venus or the ice giants Uranus and Neptune, we'll use knowledge gained from studying exoplanetary extremes. When we characterize newly discovered worlds around distant stars, we'll interpret our observations through the lens of these known cosmic extremes. The universe's deadliest worlds also feed our cultural imagination, inspiring science fiction stories and films that attempt to envision what it would be like to visit these places. While humans may never set foot on a planet where it rains molten iron, our creative works allow us to explore these environments virtually, extending our mental reach beyond the physical limitations of our species. In a cosmos filled with deadly worlds, Earth stands out not as the standard model of a planet, but as something precious, a place where the cosmic extremes are held at bay, where liquid water flows on the surface, where temperatures allow complex chemistry to flourish, and where life has had billions of years to evolve into myriad forms, including one species capable of pondering distant worlds. As that species, as humans uniquely blessed with the capacity to discover and understand these far-off places, we bear a special responsibility. We must continue exploring and studying the deadliest worlds, not just for scientific knowledge, but for the perspective they provide. And we must apply that perspective toward appreciating and preserving the remarkable habitability of our home planet. The universe's deadliest worlds are more than scientific curiosities. They are mirrors that reflect our cosmic fortune, teachers that expand our understanding, and reminders of both our vulnerability and our privilege as inhabitants of a truly habitable world. In their extremes, we find context for our existence, a framework for understanding Earth not as the cosmic standard, but as a precious island of habitability in a sea of beautiful but deadly possibilities. Our exploration of these terrifying planets also reveals something profound about human consciousness itself. We are a species that evolved on a single planet, under specific conditions, yet we've developed the capacity to understand environments we could never physically experience. Through scientific investigation, mathematical modeling, and creative imagination, we can conceptualize the glass rain on HD 189733b, the crushing depths of TRAPPIST-1d, or the permanent night of rogue planets drifting between stars. This capacity for abstract understanding might be as remarkable as the deadly worlds themselves. We've transcended our immediate sensory experience to comprehend realities vastly different from our own, a cognitive leap that allows us to map the universe beyond our direct observation. Our ability to understand these deadly worlds without experiencing them firsthand represents a kind of mental transcendence, a liberation from the limitations of our physical form. As we conclude our journey through these nightmare worlds, let us carry forward both the wonder they inspire and the perspective they provide. The universe contains horrors beyond human imagination, yes, but it also created the perfect conditions for us to evolve and develop the capacity to discover and understand those very horrors. In that remarkable fact lies perhaps the greatest wonder of all, that in a universe dominated by deadly extremes, life like ours managed not only to emerge, but to thrive to the point of comprehending worlds far beyond our reach. The deadly planets will continue their cycles of creation and destruction, indifferent to our study of them. Iron will still reign on distant worlds, glass storms will still scour alien atmospheres, and planets will still be consumed by their stars, whether we observe them or not. But by learning about these cosmic extremes, we become more than passive inhabitants of our planetary oasis. We become conscious participants in the grand cosmic story, using our unique capacity for understanding to encompass realms beyond our physical reach. And perhaps that is our special role in this universe of extremes: to observe, to understand, to appreciate both the deadly wonders beyond our world and the remarkable fortune of the world we call home. In mapping the cosmic nightmares, we better understand our cosmic blessing, Earth, our island of habitability in a sea of beautiful but deadly worlds, our perfect vantage point for exploring a universe filled with planets far more terrifying than our own.